Hello there and welcome to Physics with William, where curiosity gets cozy, the universe lowers its voice, and science takes the scenic route towards sleep. Tonight, we're going to wander into one of the strangest little corners of quantum physics, a place where light behaves as if it is keeping a secret until the universe decides whether that secret can be known. Our gentle subject is the quantum eraser, and more specifically, the delayed choice quantum eraser, an experiment with a name that sounds rather like a mysterious device someone might find in the back cupboard of a very confused laboratory. It is not a machine for rubbing out homework. It is not a time machine. It will not help you go back and unsay something awkward at dinner, which is a shame because physics could have been very useful there. But it does ask a deeply unsettling question. What if the past of a tiny particle is not fully settled until information about that past exists? Now, before we drift any deeper into photons, screens, paths, and all the odd little habits of the quantum world, I would love to know where in the world are you listening from tonight. Is it late where you are, or is the day still quietly moving around you? Perhaps you are tucked into bed. Perhaps you're sitting with a cup of tea. Perhaps you're simply letting the sound of science soften the edges of a long day. Wherever you are, it is fitting in a way, because tonight we are talking about an experiment where time itself seems to become a little slippery, where the order of things looks less solid than it does in ordinary life, and where a photon can appear to behave as if a choice made later somehow matters to what it was doing before. If you find this kind of slow journey soothing, if you enjoy letting strange ideas become gentle instead of overwhelming, then I would be grateful if you liked the video and subscribed. It helps this quiet little corner of physics reach other tired minds who may also enjoy falling asleep beside the mysteries of the universe. And as always, I do hope the topic is interesting enough to make you curious, but not so interesting that it keeps you wide awake until breakfast. Though if it does, at least you can lie there with the comforting knowledge that reality itself may be less definite than your alarm clock claims. So, settle in. Let the room around you become still. Let the day step back a little. Tonight we begin with a puzzle about light, information, and the strange possibility that nature does not simply keep a hidden record of everything that happened. Sometimes it seems nature waits to see what can be known. The quantum eraser begins with a much older mystery, one that has been troubling physicists for more than a century. It begins with light passing through two openings and landing on a screen. That may sound simple enough. In normal life, if you throw tiny grains of sand through two narrow gaps, you expect each grain to go through one gap or the other. Some grains land behind the left gap. Some grains land behind the right gap. If you did it carefully enough, you would eventually see two rough piles or two bright bands, one behind each opening. Nothing dramatic. No deep philosophical crisis, just grains being grains. But light is not sand. And when scientists send light through two narrow openings, something different appears. Instead of two simple bands, they find a pattern of alternating bright and dark stripes. This is called interference. It is the kind of pattern waves make when they overlap. If you have ever watched ripples on a pond meet each other, you have seen the basic idea. One ripple can rise with another and make a larger ripple, or one ripple can meet another in just the wrong way and flatten out. Waves can add and cancel. They can build and erase each other. So when light creates an interference pattern, it looks as if light has travelled like a wave through both openings at once, spreading out, overlapping with itself, and painting a striped pattern on the screen. For a long time, this seemed strange but manageable. Light acts like a wave. Fine. Put that in the cupboard beside other strange but accepted things, like why socks vanish in the laundry, but then experiments became more delicate. Scientists learned how to send light not as a bright beam, but one photon at a time. A photon is a single packet of light, the smallest individual piece of light we can talk about in this kind of experiment, and that is when the mystery becomes much harder to ignore. If you send one photon at a time toward the two openings, each photon lands on the screen as a tiny single dot. That seems particle-like. It arrives in one place, not smeared across the whole screen like a wave of jam on toast. One photon, one dot. Very sensible. Very. But if you keep sending photons one after another, slowly, patiently, perhaps with the quiet determination of someone waiting for a kettle that refuses to boil, the dots begin to build up. And after many photons have landed, the interference pattern appears again, bright and dark bands, a wave pattern, even though each photon arrived alone. This is the part where ordinary intuition quietly puts on its coat and leaves the room. How can a single photon interfere with itself? Did it go through both openings at once? Did it somehow explore both possible paths as a wave, then choose one landing place when it arrived? Or did it secretly go through only one opening, while still producing the pattern of something that went through both? The double-slit experiment does not merely show that light is strange, it shows that the very question of what the photon did may not have a normal answer. The natural response is to say, well, let us check. Let us put a detector near the openings and see which path the photon takes. That sounds reasonable. If the photon is playing a little quantum trick, surely catching it in the act should clear things up. So scientists do exactly that. They arrange the experiment so that they can know whether the photon went through one opening or the other, and as soon as that which way information becomes available, the interference pattern disappears. The photons now build up a pattern more like ordinary particles. They behave as if each one went through one path, not both. At first glance, this sounds like the photon notices it is being watched and decides to behave properly, like a child sitting up straight when a teacher enters the room. This is a tempting image, but it is also misleading. In quantum physics, observation does not need to mean a person staring dramatically at a screen with raised eyebrows. It does not mean consciousness reaches out and pokes reality into shape. It means that information about the system becomes physically available somewhere in the world. A detector, a mark, a trace, a tiny physical record of which path the photon took. Once that information exists, the wave-like interference is lost. This is already strange enough, but the delayed choice quantum eraser takes the strangeness and turns it gently, like a key in a lock. It asks what happens if the decision about whether path information exists is made after the photon has already landed on the screen. That is the heart of the puzzle. The photon reaches the screen first. Its dot is already there. Later, another part of the experiment decides whether the which way information is preserved or erased. And depending on how the later information is sorted, the earlier photon dots reveal either particle-like behavior or wave-like interference. Now that sentence can sound as if the future is changing the past. It can sound as if the photon lands first, then waits for instructions from later, perhaps checking its little photon diary and editing the previous page. But we need to move carefully here, because the quantum eraser is strange enough without adding extra magic to it. The experiment does not allow anyone to send messages backward in time. It does not allow the future to be changed like a film scene being reshot. It does not mean a human mind decides what reality was by choosing what to look at after the fact. The truth is subtler, and in some ways more unsettling. The experiment suggests that at the quantum level, reality is not always built from definite little stories hidden underneath the surface. It may be built from relationships, information, and correlations that only become clear when the full arrangement is known. Imagine, very gently, that you are reading a mystery novel, but the pages are mixed with another copy of the same story. Some pages tell one version. Some pages tell another. If you look at all the pages in a pile, you may see only confusion. But if someone later sorts them according to a hidden clue, patterns appear that were not obvious before. The later sorting does not rewrite the ink already printed on the paper. The pages were already there, but the meaning of the pattern only appears when the right information is used. The delayed choice quantum eraser is not exactly like that, but it gives us a soft doorway into the idea. The photon marks on the screen are not being changed after they arrive. What changes is how those marks are correlated with information held by their entangled partners. Entanglement is another word we'll meet properly as we continue. For now, think of it as a special quantum link between particles, a connection so deep that the particles cannot be described as fully separate objects with fully separate stories. If two photons are entangled, measuring one can reveal something about the other, not because a little signal runs between them like a frantic messenger with a clipboard, but because the pair belongs to one shared quantum description. They are not two ordinary marbles flying apart. They are more like 2 pages from the same very odd book. In the delayed choice quantum eraser, one photon goes toward a screen. Its partner photon travels a different route, toward detectors that may preserve or erase which-way information. The first photon lands before the later measurement is completed. The dot appears. Nothing visibly dramatic happens. If you watch only the main screen, you do not see a clean interference pattern appear by itself. You see what looks like a scattered pattern, a kind of mixture. But when scientists later compare those dots with the results from the partner photons, they can sort the data into groups. Some groups show interference. Other groups show the opposite kind of interference. Other groups show particle-like behavior. The pattern was not visible in the unsorted pile, but it emerges in the correlations. This is why the experiment is so difficult to explain without accidentally making it sound like a science fiction machine. The phrase quantum eraser feels as if something is being rubbed out, and in a sense, information is being made unavailable. But the erasing is not like wiping a memory from the universe with a cosmic cloth. It is more precise than that. It means that the experiment is arranged so there is no longer any physical way to know which path the photon took. When path information is available, interference is gone. When path information is erased, the wave-like pattern can be recovered in the carefully sorted results. The part that makes people sit up, even if they were nearly asleep, is the delayed choice. The erasing can happen after the photon has already landed. This seems backwards. In everyday life, causes come before effects. You switch on the lamp, then the room becomes bright. You put bread in the toaster, then toast appears, unless the toaster is feeling rebellious. You decide something, then consequences follow. But quantum experiments do not always fit neatly into the ordinary story of before and after. They do not break causality in the simple sense. They do not let us send usable information into yesterday. But they do make us question whether the photon had a definite path in the ordinary way before the measurement context made such a path meaningful. That is perhaps the quietest and deepest point of all. The quantum eraser does not simply say that the past changes. It asks whether the past of a quantum object was ever a settled classical story in the first place. When we say the photon went through this opening or that opening, we may be forcing everyday language onto a situation where everyday language does not fit. The photon may not have had a definite path waiting quietly in the background. Instead, what becomes real in the experiment depends on what information exists, what can be known in principle, and how the quantum system is connected to the measuring arrangement. This can feel uncomfortable because we're used to a universe that keeps records even when no one looks. If a cat walks across a garden at night, we assume it took one path across the grass, even if nobody saw it. If a letter passes through a mail slot, we assume it went through one particular opening at one particular time, even if we were making tea in the other room. The world of chairs, cats, letters, and slightly overfilled mugs behaves as though it has definite histories, and for all practical purposes it does. Quantum uncertainty does not make your sofa appear in 2 rooms at once, which is good news for furniture planning. But photons are not cats. Electrons are not letters. Tiny quantum systems do not always carry definite classical facts before measurement. They carry possibilities, and those possibilities can interfere. The act of making which way information available changes the situation, not because the photon is embarrassed, but because the quantum alternatives no longer combine in the same way. Information matters, not information as a thought floating in someone's mind, but information as a physical feature of the universe, a record, a trace, a correlation, a fact that could in principle be found. So tonight, as we begin this slow walk into the delayed choice quantum eraser, it may help to keep one gentle rule in mind. The experiment is not telling us that we can change the past whenever we please. It's telling us that at the smallest scales, the past may not be made from the same kind of fixed little events we imagine. The universe may not write every detail into a hidden notebook in advance. Some details become real only when the conditions for knowing them are in place. And when those conditions are changed, the story we are allowed to tell changes too. That is what makes the quantum eraser so fascinating. It sits at the edge between physics and philosophy, between what can be measured and what can be said. It reminds us that reality is not always made of tiny billiard balls rolling through invisible tracks. Sometimes it is made of waves of possibility. Sometimes the difference between a wave and a particle is not about what the thing secretly is, but about what the world has allowed to be known about it. And sometimes, when the information is delayed, erased, or entangled with something far away, the neat timeline in our heads begins to wobble like a sleepy table with one short leg. Still, there is something peaceful about this mystery. It does not shout. It does not explode across the sky. It happens in quiet laboratories, in carefully aligned beams of light, in faint clicks of detectors, in data sorted patiently after the fact. The universe, in this case, whispers its weirdness. A photon lands, another photon is measured, a pattern appears only when the right pairs are brought together, and from those tiny marks we are led toward a question so large it almost disappears into the dark. Does reality have a definite past before it is measured, or does the past become definite only through the information the universe keeps? So let your thoughts slow around that question, not in a tense way. No need to solve it all at once. Physics itself has not finished wrestling with it, and physics has had quite a few clever people and a great many cups of coffee. For now, we only need to step into the puzzle carefully. First, we will return to the simpler double-slit experiment, the old doorway through which this entire mystery first entered science. We will watch light behave like a wave, then like a particle, then like something that refuses to fit comfortably into either word, and from there, little by little, the quantum eraser will begin to make its strange kind of sense. To understand why the quantum eraser feels so strange, we need to return to the older experiment that first opened the door. It is one of the simplest looking experiments in all of physics, and also one of the most stubbornly mysterious. There is a source of light, a barrier with two narrow openings and a screen placed behind it. That is nearly all. No giant telescope, no roaring particle collider, no enormous machine humming under a mountain, just light, two slits, and a place for the light to land. It sounds almost too small to trouble the foundations of reality. And yet, from this quiet arrangement, physics learned that nature does not always behave like the sensible world we thought we knew. Imagine for a moment that you are standing in a calm room with a wall in front of you. The wall has two narrow vertical openings cut into it side by side. Behind the wall is another surface where anything passing through the openings can leave a mark. If you were throwing tiny pebbles at the wall, you would not expect anything especially surprising. Some pebbles would hit the wall and bounce away. Some would pass through the left opening. Some would pass through the right opening. And on the surface behind the wall, you would eventually see two main patches where the pebbles had landed. One lined up with the left opening and one lined up with the right. Pebbles are not known for philosophical subtlety. They go where they go. They do not pause halfway through the air to consider whether they are secretly a wave. Now imagine doing the same sort of thing with water waves. Instead of pebbles, picture ripples moving across the surface of a shallow pond toward a barrier with two narrow gaps. When the ripples reach the barrier, each gap acts like a new source of ripples. The two sets of waves spread out from the openings and overlap with one another. In some places, crest meets crest and the water rises higher. In other places, crest meets trough and the water flattens out. The result is not two simple bands behind the openings. It is a pattern of strong and weak motion, a series of places where the waves add together and places where they cancel. This kind of pattern is called interference. It is one of the familiar fingerprints of waves. So far, everything is comfortable. Pebbles make two bands, waves make interference. The trouble begins when light is brought into the room. For a long time, people argued about what light really was. Was it made of particles, tiny bits travelling in straight lines? Or was it a wave, spreading and bending and overlapping like ripples? Isaac Newton favoured a particle view of light. Later scientists found powerful evidence that light behaved like a wave. The double-slit experiment became one of the clearest demonstrations. When a beam of light was sent through two narrow openings, it created an interference pattern on the screen. Bright stripes appeared where the waves reinforced one another. Dark stripes appeared where they cancelled. Light, it seemed, was a wave. That would have been strange enough, but also tidy. Science likes tidy answers. Light is a wave. Place it on the shelf, label it carefully and move on. But nature was not finished being inconvenient. In the early 20th century, as quantum theory began to take shape, physicists found that light also behaved like particles in certain situations. Light came in discrete packets, later called photons. These photons could strike a surface one at a time. They could knock electrons loose from metal. They could arrive as individual events like tiny taps rather than one continuous stream. So light was not simply a wave in the old sense. It had particle-like behaviour too. At first, this may sound like light is just switching costumes. Sometimes it dresses as a wave, sometimes as a particle, depending on the occasion. A little theatrical perhaps, but manageable. The double-slit experiment, however, makes the situation much harder to explain. Because if we send photons through the two slits one at a time, so that only a single photon is in the experiment at any given moment, each photon still lands on the screen as a single dot. One photon, one tiny mark. That looks particle-like. It does not spread itself as a visible smear across the entire screen. It does not leave half a dot here and half a dot there, as if it forgot to pack properly before travelling. But if we keep sending photons one by one, the dots slowly build up. At first they look random, scattered, almost meaningless. Then, after many photons have arrived, the pattern emerges. Not two simple bands, not the pattern of pebbles. The dots arrange themselves into bright and dark stripes, the interference pattern of a wave. One photon at a time, with nothing obvious for each photon to interfere with, light still builds the pattern of something interfering. This is the moment where the double slit stops being a simple experiment and becomes a kind of quiet riddle. If each photon is sent alone, what is it interfering with? It cannot be colliding with another photon, because there is no other photon there at the same time. It cannot simply be a tiny pellet passing through one slit in the ordinary way, because ordinary pellets build two bands, not an interference pattern. The result suggests that each photon behaves as though it explores both possible paths through the experiment. It is not correct to imagine it as a small glowing marble secretly choosing left or right, while also somehow leaving the wave pattern behind. At the quantum level, before measurement, the photon is described by a spread of possibilities. Those possibilities pass through the openings, overlap and interfere. Then, when the photon is detected on the screen, the result is a single definite mark. This is easy to say and difficult to truly picture. Our minds are built from everyday experience. We know about thrown balls, falling leaves, spilled tea, and the way a biscuit either remains on the plate or has mysteriously vanished. We're used to objects having definite locations and histories. A tennis ball does not pass through two doors at once, unless someone has done something very unfortunate to the tennis ball. A person walking through a hallway does not take two separate routes and interfere with themselves before arriving at the kitchen. The quantum world does not scale neatly into the ordinary world. It has rules that are deeply reliable in experiments, but deeply unfamiliar to imagination. One helpful way to think about the photon is not as a tiny bead with a hidden root, but as a quantum object whose possible outcomes are spread out until the measurement gives one result. The photon does not behave like a classical object with a fully known little path waiting underneath our ignorance. It behaves according to a wave of possibility. That wave is not simply a water wave or a sound wave. It is not a physical ripple in air or liquid. It is a mathematical description of possible outcomes, and yet its effects are real enough to paint an interference pattern across a screen. If that feels slippery, that is because it is. Quantum physics often works perfectly while refusing to become comfortable. Now naturally, anyone seeing this mystery wants to ask the obvious question: which slit did the photon actually go through? It is a fair question. It is the kind of question ordinary curiosity asks before breakfast. If we do not know whether the photon went through the left opening or the right one, let us place a detector near the openings and find out. Let us watch more carefully. Surely once we catch the photon in the act, the mystery will clear. And in a way it does, but not in the way we hoped. When the experiment is changed so that we can determine which slit the photon went through, the interference pattern disappears. The photons no longer build the pattern of overlapping possibilities. Instead, they behave more like ordinary particles, producing the kind of result we would expect if each photon passed through one path or the other. The act of making path information available changes what can happen. Again, this does not mean a person has to stare at the slits with intense concentration. It does not mean human consciousness is casting spells on light. A detector, an interaction, a physical record is enough. If the path can be known in principle, the wave-like interference is lost. This is one of the most important lessons of the double-slit experiment. It is not simply that photons are sometimes waves and sometimes particles. It is that the experimental arrangement decides which kind of behavior can appear. If the arrangement allows the alternatives to remain indistinguishable, the photon behaves in a wave-like way, and interference appears. If the arrangement makes the alternatives distinguishable, if the universe carries a record of which path was taken, the interference disappears. Information is not just something we learn after the fact. At the quantum level, information is part of the physical situation. That idea takes some getting used to. In ordinary life, we tend to think of information as passive. Suppose you walk through one of two doors and someone checks a security camera later. The checking does not change which door you used. The door was already used. The camera simply reveals a fact that existed all along. But in the quantum experiment, path information is not merely a convenient note about a definite hidden journey. The existence of that information changes whether the alternatives can interfere. If the left and right possibilities become physically marked in any way, they no longer combine as wave alternatives. The photon behaves as if the choice has become definite. This is why the double-slit experiment can feel almost personal, as if the photon knows when it's being watched. But that is not quite right. The photon does not have a tiny sense of embarrassment. It does not become shy under observation. Measurement in quantum physics is not necessarily about awareness, it is about interaction. To measure something, the quantum system must become linked with another physical system, a detector, a screen, a molecule, an environment. That linking can create a record, and once a record exists, even a tiny one, the delicate wave-like alternatives stop interfering in the same way. The world becomes more classical, more definite, more like the one we're used to. There is a useful comparison here, though like all comparisons in quantum physics, it must be handled gently. Imagine two stories being told at once, so perfectly blended that you cannot tell which line came from which story. Their meanings overlap, reinforce, and confuse each other. But then someone marks every sentence with a label showing which story it came from. Once the labels are there, the blending is gone. You can separate them. The combined effect changes. The labels do not need a human reader immediately, they only need to exist. In the double-slit experiment, path information works a little like that. If the alternatives are labelled by the physical world, interference fades. But we should be careful not to turn this into a simple trick. The disappearance of interference is not caused by clumsy disturbance alone, at least not in the naive sense of a detector bumping the photon and ruining the result. Early explanations often made it sound as if observing the photon simply knocks it about, like trying to check a soap bubble with a boxing glove. there is some truth in the fact that measurement requires interaction. But the deeper issue is not merely physical disturbance, it is distinguishability. If the experiment contains a way, even in principle, to tell which path the photon took, then the alternatives cannot interfere in the same way. If the paths remain indistinguishable, interference can appear. This distinction matters because it leads directly toward the quantum eraser. The quantum eraser asks what happens if path information is first made available, but then erased, not in a casual sense, but in a precise quantum sense where the alternatives become indistinguishable again. Can interference return? The answer is yes, under the right conditions, and if that erasing happens after the photon has already been detected, the experiment becomes the delayed choice quantum eraser, the puzzle waiting for us beyond the double slit. Before going there, though, it is worth staying a little longer with the original mystery, because it contains almost everything we need. The double slit experiment tells us that quantum objects do not behave like tiny ordinary things moving along hidden tracks. When unmeasured, their possibilities can overlap and interfere. When path information exists, interference disappears. When a photon is finally detected, it appears as a single event, wave-like spread before detection, particle-like arrival at detection, not because the photon is literally a water wave that suddenly becomes a marble, but because those words, wave and particle, are borrowed from our everyday world and used to describe different aspects of something deeper. This is sometimes called wave-particle duality, though that phrase can create its own confusion. It can make it sound as if the photon is half wave and half particle, or switching between two costumes backstage. But a photon is not a little object trying to decide which human category it prefers. It is a quantum object. It behaves according to quantum rules. In some experiments, its behavior resembles what we call a wave. In others, it resembles what we call a particle. The problem is not that the photon is confused. The problem is that our language grew up in a world of stones and water, not in a world of probability amplitudes and measurement contexts. Physics gives us the predictions. Our imagination struggles to dress them in familiar clothes. The double slit also reveals something profound about reality and knowledge. In the classical view, not knowing something usually means the fact exists, but we lack access to it. If you lose your keys, they are somewhere. Their location is definite, even if your memory is not cooperating. They might be under a book, in a coat pocket, or somehow in the refrigerator, which is always a worrying discovery. But quantum uncertainty is not merely lost keys uncertainty. It is not simply that the photon has a definite path and we are ignorant of it. The interference pattern tells us that treating the photon as if it secretly chose a single path does not capture what is happening. The possibilities themselves matter. That is the part that makes the experiment so quietly radical. It challenges the idea that the world is always made from definite facts waiting to be uncovered. At least for tiny quantum systems, some facts do not seem to exist in the ordinary definite way until the right measurement is made. Before that, the system is described by a range of possible outcomes. These possibilities are not imaginary in the everyday sense. They have measurable consequences. They can add, cancel, and create patterns. The interference stripes on the screen are not philosophical decoration. They are the physical signature of possibilities behaving like something real. And yet, when a photon lands, it lands in one place. This is another part of the puzzle. The wave-like description spreads through the experiment, but the detection is local and definite. A tiny spot appears on the screen, then another, then another. No one sees half a photon politely dividing itself between two bright bands. The screen records single events. But the distribution of those events over time follows the interference pattern. The individual result is unpredictable. The overall pattern is highly reliable. Quantum physics is not random chaos. It is probability with exquisite discipline. The universe may not tell us where the next photon will land, but it tells us with remarkable accuracy how many will land in each region after enough have arrived. There is something almost humbling in that. The double-slit experiment does not give us control over every individual event. It gives us a pattern born from uncertainty. It says that nature can be deeply lawful without being fully predictable in the old classical sense. The old dream was that if we knew every detail of a system, we could calculate the future exactly. The quantum world softens that dream. It does not throw away order. It gives us a different kind of order, one based on probabilities, interference, and measurement. This is why the experiment has become so famous. It is not because the equipment is visually dramatic. It is because the meaning is so large. In a quiet arrangement of slits and screens, we meet a universe that does not behave as though all its tiny details are settled in advance. We meet a universe where what can be known changes what can be observed. We meet a universe where the same photon can help build a wave pattern when its path is unknowable, and a particle-like pattern when its path is marked. The experiment is small, but the question it opens is enormous. What is reality doing when we are not measuring it? Of course, physicists have many interpretations of quantum mechanics, and they do not all tell the story in the same way. Some interpretations speak of collapse, where measurement turns a spread of possibilities into one outcome. Others speak of branching worlds, where all possible outcomes occur in different branches of reality. Others focus on information, relationships, or the role of the measuring apparatus. These interpretations differ in their pictures of what is really happening underneath the equations. But the experimental facts remain. When the paths are indistinguishable, interference appears. When path information is available, interference disappears. The double slit stands there, calm and irritatingly patient, asking each interpretation to explain itself. For our journey, we do not need to choose a final interpretation tonight. That would be rather ambitious for a sleepy science video, and perhaps unfair to anyone already half drifting under a blanket. What matters is the pattern of behaviour. The double slit shows us that quantum reality is sensitive to whether alternatives can be distinguished. It teaches us that information is not an optional extra added to physics later. It is built into the way quantum systems behave, and it prepares us for the next twist, where scientists do not merely observe or avoid observing a photon path, but arrange for path information to be preserved, hidden, erased, and delayed. The double slit is often described as the central mystery of quantum mechanics, and that description is not far from the truth. It contains the whole strange flavour of the subject, a simple setup, a surprising result, a clash between what common sense expects and what nature actually does. If you cover one slit, the pattern changes. If you leave both open and do not mark the path, interference appears. If you mark the path, even gently, the interference goes away. The photon seems to answer not the question we wish it had answered, but the question the experiment actually asks. That last point is important. In quantum physics, an experiment is not just a passive window onto reality. It is part of the question being asked. The way we set up the apparatus determines which aspect of the quantum system can show itself. Ask for wave-like behaviour by allowing alternatives to remain indistinguishable, and interference can appear. Ask for path information, and the particle-like aspect appears instead. It is not that the photon lies. It is that the answer depends on the question. A little like asking someone whether they are a morning person at 6 in the morning. The answer you get may depend strongly on the conditions of measurement. So, as we move toward the quantum eraser, keep the double slit in mind as the first doorway. Light passes through two openings. If no record exists of the path, it builds a pattern that only waves should make. If a record exists, it behaves as though it took one route. The mystery is not just in the photon, but in the relationship between the photon, the possible paths, the measuring device, and the information available to the world. The double slit does not yet rewrite the past or seem to. It does not yet delay the choice until after the photon arrives. But it gives us the essential ingredients: a quantum object, two possible paths, an interference pattern, a path record, and the startling fact that knowing, or being able to know, changes the pattern nature allows us to see. From here, the next step is to look more closely at the photon itself, and at why it refuses to fit neatly into the familiar boxes marked wave and particle. Because once we understand that the photon is not simply one or the other, but something more delicate than both words can hold, the later puzzle of the eraser begins to feel less like a trick and more like a careful experiment revealing the hidden grammar of the quantum world. A photon is a very small thing to carry such a large mystery. It has no little surface you could polish, no tiny paint mark you could follow through the air, no miniature nose pointing bravely toward the future. It's not a grain of dust, not a spark in the ordinary sense, not a glowing bead sailing through space like a firefly with excellent punctuality. And yet, every lamp in your room, every sunset on a window, every glimmer from a phone screen, and every star that has ever found its way into a human eye depends on photons. They are the carriers of light, and light is so familiar to us that we often forget how strange it really is. In everyday life, light feels simple. You switch on a lamp and the room becomes brighter. You open the curtains and morning walks in. You shine a torch down a hallway and the beam seems to travel in a straight line, obedient and sensible, like it knows exactly where it is going. But underneath that ordinary brightness is a quantum object that refuses to behave like anything our hands can hold. The photon is not quite a wave in the way water is a wave. It is not quite a particle in the way a pebble is a particle. It is something deeper, something that can show wave-like behavior or particle-like behavior depending on how the universe is asked to reveal it. That little phrase, depending on how it is asked, is where the trouble begins. In normal experience, a thing is what it is whether we ask about it carefully or not. A mug on a table remains a mug if you look at it from the left side, the right side, or with one eye half closed because you are still waking up. It does not become soup just because the question was phrased differently. But the photon is not a mug. It belongs to a layer of reality where the kind of experiment we perform is not just a passive way of collecting facts. The experiment helps define which facts can appear. When we send photons through the double slit without trying to learn which opening each one uses, the overall pattern looks wave-like. One by one, the photons land as tiny dots, but over time those dots build up into interference stripes. This tells us that something about the photon's possible paths is combining. The two routes through the slits are not behaving like two separate roads taken by little pellets. They are behaving like alternatives that can overlap, strengthen and cancel. The photon seems to travel as a spread of possibility, not as a tiny object with a fixed route hidden behind our ignorance. But when we add a way to know the path, the pattern changes. If the experiment is arranged so that the photon leaves behind a trace of which slit it used, then the interference disappears. The same photon, the same two openings, the same screen, and yet the behavior is different. Not because the photon has grown tired of being mysterious, not because it has noticed a physicist nearby and decided to tidy itself up. The change happens because the physical situation has changed. The two paths are no longer indistinguishable. The universe now carries information that separates them. This is the strange choice between wave and particle. It is not a choice the photon makes in the way you might choose tea over coffee, or the slightly larger slice of cake while pretending you did not notice it was larger. It is a choice created by the structure of the experiment. If the paths remain unmarked, the photon's alternatives can interfere, and the wave-like pattern appears. If the paths are marked, the alternatives are separated, and the photon behaves more like a particle that went one way or the other. The photon does not reveal a single fixed identity. It reveals an aspect of itself according to the question nature is being asked. This can be very hard to accept, because we naturally want to imagine a hidden little story. We want to say that the photon really went through the left slit or really went through the right slit, and the interference pattern is just some clever effect we have not yet understood. That would be more comfortable. It would let us keep the familiar picture of objects travelling through the world along definite paths. But experiments keep pressing us away from that comfort. The interference pattern is not what we expect if the photon secretly chooses one slit while we are simply unaware of it. The mathematics and the measurements tell us that the unmeasured photon is not merely hiding a classical route. It is described by several possible routes that remain linked until the experiment forces a particular kind of answer. A path sounds like such a simple idea. We use paths constantly. A path through a garden, a path home from the shops, a path of a falling leaf, twisting slowly toward the ground. A path is just the route something takes from one place to another. If a bird flies across the sky, we can imagine tracing its flight. If a marble rolls across a table, we can mark where it was at each moment. Even if we do not watch carefully, we assume the path was there. The marble did not pause between 2 points and become undecided about its own existence. It rolled somewhere. It had a route. Quantum paths are not so straightforward. When we talk about the path of a photon in the double-slit experiment, we're using everyday language in a place where everyday language begins to creak. Before measurement, the photon is not simply following a neat little track like a train on rails. Its behavior is described by a range of possible ways it could be found. These possibilities are not just empty guesses in our heads. They can combine and produce observable effects. The interference pattern is the evidence. If the possibilities were not physically meaningful in some way, they could not cancel and reinforce one another to shape where photons eventually land. Here is a gentle way to picture it, though every picture is imperfect. Imagine that the photon is not travelling as a tiny bead, but as a question spreading through the experiment. The question reaches both slits. The possible answers overlap beyond them. Then the screen gives one definite reply, a small dot in one place. But that dot is not produced by a classical path alone. It is produced by the whole arrangement of possibilities. Over many repeated photons, the replies form a pattern that reflects the hidden structure of the question. When both slits are open and unmarked, the question includes both routes. When one route is marked, the question changes. The answer changes with it. This is why physicists are careful when they say a photon went through both slits. That phrase is useful, but it can also mislead. It may make us imagine the photon splitting into two little halves, one squeezing through the left slit and one through the right, then meeting up again like two very tiny hikers comparing notes. But photons are not little physical blobs dividing and rejoining. The better idea is that the quantum state includes both alternatives. The possibilities associated with the two slits remain coherent, which means they can interfere. Coherence is a kind of delicate togetherness between alternatives. It is easily lost when information leaks into the environment. The word leaks is important. Path information does not have to be recorded in a big obvious way. It does not need a dramatic screen-flashing left slit or right slit in large letters, which would admittedly make laboratory work more theatrical. A faint interaction can be enough. If some part of the environment becomes correlated with the path, if a detector, atom or photon carries away a trace that could reveal which route was taken, then the two alternatives are no longer fully blended. The interference fades. The quantum system has become entangled with the measuring device or the environment, and the wave-like possibilities no longer combine in the same visible way. That process is part of why the world around us seems so definite. Big objects are constantly interacting with their surroundings. A chair is being touched by air molecules, warmed by light, tugged by gravity, and generally bothered by the universe at every moment. Its quantum possibilities are not isolated enough to interfere in noticeable ways. The environment is continually gathering information about where the chair is, so the chair appears classical, solid, and unambiguous. It does not create an interference pattern across your living room, which is considerate of it. Tiny particles, by contrast, can be isolated well enough for their possibilities to remain coherent. That is why photons and electrons can behave in ways chairs do not. Still, even with photons, the wave and particle language can create a false drama. It sounds as though nature has two separate modes and flips between them. Wave mode for interference, particle mode for detection. But the photon itself is not really either in the old classical sense. Wave and particle are human categories, born from the familiar world. A photon is a quantum excitation of the electromagnetic field, though that phrase is rather less cosy than tiny packet of light. It does not need to be squeezed into one classical box. Instead, the photon has properties that show up differently depending on the measurement. It can spread in possibility and arrive in a point-like event. Both are true, but neither is the whole story. Think of a coin spinning on a table. While it spins, it is not simply heads or tails in the usual resting sense. It is a blur of both possibilities, and only when it falls do you get one definite result. This comparison is not exact, because a spinning coin still has a definite physical state in the classical sense, and a photon's quantum state is much stranger. But the coin helps with one idea. Sometimes the question is not answered until the conditions force an answer. The photon's landing spot is definite when it is detected, but before that, its behavior cannot be fully captured by saying it was just a tiny object on a single hidden road. The photon's path, then, is not something we can always talk about in ordinary terms. In some experiments, a path becomes a meaningful thing. If we place detectors so that path information exists, we can say the photon was found along one route. In other experiments, the idea of a single path is not part of the correct description. The alternatives remain open, and interference tells us they were never simply separate classical journeys. This is the delicate shift that prepares us for the quantum eraser, because the eraser does not merely ask whether a photon went left or right. It asks what happens when the very possibility of knowing left or right is created, then removed. There is a temptation to imagine the photon as cunning, as if it somehow senses the future plan of the experiment and behaves accordingly. This idea is memorable, but it is not the best way to think about it. The photon is not peeking ahead at the apparatus. It is not reading the laboratory schedule. It does not know that a graduate student has not slept properly and is about to adjust a detector. What matters is the full quantum arrangement. The photon, the slits, the detectors, the environment, and any entangle partner are all part of the physical description. The result depends on what kinds of information are preserved and what kinds are made unavailable. Information sounds almost too ordinary for such a strange role. We use information to mean facts, notes, messages, labels, things written in notebooks, or muttered by someone who has read one article and now considers themselves an expert. In quantum physics, information has a stricter meaning. It is physical. It means that a system carries a trace that can distinguish between alternatives. If a detector ends up in one state when the photon goes one way and another state when the photon goes the other way, then the detector holds path information. Even if no human reads it, even if the data sits quietly in a machine, even if everyone in the room has gone for a sandwich. This physical view of information changes the double slit from a simple puzzle about observation into a deeper puzzle about reality itself. The photon's wave-like behavior depends on whether the alternatives are indistinguishable. The particle-like behavior appears when the alternatives are distinguished. So the key question becomes not what does the photon secretly look like, but what distinctions does the universe preserve? What records exist? What can be known, even in principle? The answer to those questions shapes the pattern on the screen. This is why the delayed choice quantum eraser feels so unsettling. It plays with the timing of those records. In the basic double slit, path information is either available or not available, while the photon passes through the slits. That is strange, but at least it sounds orderly. First, the photon travels, then the detector either marks the path or does not. Then the screen records the result. But in the delayed choice version, the path information may be dealt with after the photon has already arrived at its detector. The timing seems to challenge our usual cause and effect story. How can a later choice about information affect whether the earlier photon belongs to a wave-like or particle-like pattern? The answer will not be as simple as the future changing the past. That phrase is attractive, but physics is rarely kind to attractive phrases that run too quickly. The better answer has to do with correlations. The photon that lands on the screen may be entangled with another photon. The full pattern only emerges when scientists compare the first photon's landing position with what later happened to the second photon. The interference is not visible as a message on the first screen by itself. It is recovered from the sorted relationships between paired events. That may sound less dramatic than rewriting yesterday, but it is still deeply strange. The universe seems to care not only about events, but about how events are connected. Before the eraser enters, it helps to hold the photon in this careful middle place. Not a classical wave spreading like water. Not a classical particle flying like a speck of dust. Not a tiny conscious traveller making choices at the slits. A photon is a quantum object whose possible paths can behave coherently when no path information exists, and whose behaviour becomes particle-like when path information is preserved. Its path is not always a pre-written line through space. Sometimes the path is a question that only becomes answerable when the experiment is arranged to ask for it. This does not mean reality is soft in the everyday world. It does not mean you can erase your memory of eating the last biscuit and restore the biscuit to the tin, though many of us would welcome research in that direction. It means that at the smallest scales, the connection between reality and information is more intimate than common sense expects. What can be known is not just a detail added after the fact. It helps determine which pattern nature displays. The photon is not merely travelling through space. It is participating in a quantum arrangement where possibilities, records and measurements are woven together. And perhaps this is the first truly unsettling lesson on the road to the quantum eraser. We began by asking whether the photon is a wave or a particle, but the experiment gently refuses the question. It answers instead that the photon behaves wave-like when its possible paths are allowed to remain together, and particle-like when those paths are separated by information. The photon does not have to pick one identity for our comfort. Nature is under no obligation to use the categories we find easy. It gives us patterns, detections, correlations and rules that work with extraordinary precision, even when the story behind them refuses to sit still. So as we follow the photon toward the next part of the puzzle, we should carry this with us. A path is not always a fact waiting in secret. A wave is not always a physical ripple. A particle is not always a little marble. In quantum physics, these words are handles, useful for holding parts of the mystery, but not large enough to hold all of it. The double slit shows us that when paths are unknowable, light can behave as though it took both possibilities together. When path information appears, the interference is lost, and the photon takes on the face of a particle. Now the question becomes sharper. What exactly counts as path information? How small can the clue be? And what happens if that clue is hidden, scrambled or erased before anyone can use it? In the double slit experiment, the mystery does not begin with the photon landing on the screen. It begins earlier, in the quiet question of whether the photon left a clue behind. This clue may be incredibly small. It does not need to be a flashing sign. It does not need to be a loud click in the laboratory, or a scientist leaning forward and whispering, "Aha, left slit," as though catching a photon sneaking out after curfew. It only needs to be a physical trace, some mark in the world that could in principle tell us which path the photon took. That tiny clue is called which-way information, and in quantum physics it can change everything. At first, which-way information sounds harmless. It sounds like a note in the margin. If something went through one of two openings, why should it matter whether a clue exists? In ordinary life, it does not. If you walk through one of two doors, the fact that a camera records you does not change the door you used. If nobody records you, you still went through one door. Your path does not depend on whether the world wrote it down. You may not remember where you left your keys, but the keys are still somewhere, quietly waiting to be blamed on someone else. Classical reality feels like that. Facts exist whether or not we know them. The quantum world refuses to be so simple. In the double slit experiment, the photon does not merely hide a definite route from us. When no which-way information exists, its possible routes through the two slits can remain linked together. They can interfere, The photon behaves in a wave-like way, and over many repeated photons the interference pattern appears on the screen. But if the experiment is arranged so that the path could be known, even if no human being actually checks the result, that wave-like pattern disappears. The photon behaves as if it has taken one path or the other. The existence of the clue changes the pattern nature allows. This is one of the most difficult lessons in quantum mechanics, because it seems to make knowledge active. We're used to thinking of knowledge as something passive, something that arrives after events have already happened. A detective finds a footprint, and the footprint reveals where someone walked. The footprint did not create the walk. It did not reach backward and decide which hallway the person used. It simply preserves evidence. But in the quantum case, evidence is not just a passive afterthought. The possibility of evidence changes whether the different alternatives can interfere. To see why, let us return to the two paths. A photon approaches the barrier where two narrow openings wait. If both openings are available and nothing marks the route, the photon is described by two possible alternatives that remain indistinguishable. The left path and the right path are not separate classical stories. They are parts of one quantum possibility structure. Because they are not marked apart, they can overlap, combine, and produce interference. The screen eventually records one dot, but over many dots the interference pattern appears. Now place a detector near the slits. The detector does not have to shout. It only needs to become correlated with the photon's path. If the photon goes one way, the detector ends up in one state. If the photon goes the other way, it ends up in another state. That difference is a record. The world now contains a physical distinction between the two alternatives. The left route and the right route are no longer blended in the same way. They have been labelled. Once the alternatives are labelled, the interference disappears. A label may sound like an abstract thing, but in physics, a label must be physical. It could be a change in a detector. It could be another photon scattered in a particular direction. It could be a tiny change in the environment. The point is not that someone reads the label. The point is that the label exists. It means the two possible routes have become distinguishable. The quantum alternatives cannot behave as though they are one coherent whole if the universe has stored a clue that separates them. This is why quantum observation is often misunderstood. People hear that observation affects reality, and they imagine a human mind causing the photon to choose a path. It is a dramatic idea, and it has been very popular in late-night conversations, suspicious documentaries, and the sort of books that place the word consciousness rather close to the word universe. But the physics does not require a human observer. A measuring device is enough. A dust particle can become part of the environment. A stray photon can carry away information. A record can exist even if nobody looks at it. In quantum mechanics, observation is not about awareness. It is about interaction and information. That may sound less magical, but it is still deeply strange. The photon does not care whether we personally know the path. It cares, if we can use that word gently, whether the path is knowable in the physical structure of the experiment. If a record exists somewhere, interference is lost. If no record exists, interference can remain. This makes which-way information one of the key ideas in the whole quantum eraser story. The eraser is not raising a human memory. It is not deleting a thought from a physicist's mind. It is removing the physical distinguishability between alternatives so that the wave-like pattern can be recovered in the right kind of data. Imagine two musical notes played together. If they are perfectly blended, you may hear a combined sound, a pattern created by their overlap. But if each note is separated into different speakers, labelled, isolated, and recorded in a way that lets you distinguish them completely, the combined experience changes. This is only an analogy, of course. Photons are not musical notes, and quantum interference is not simply sound. But the idea of indistinguishability matters. When the alternatives cannot be told apart, they can act together. When they can be told apart, they stop producing the same combined pattern. The word indistinguishable is doing a lot of work here. It does not mean that we personally fail to distinguish the paths because we are lazy, distracted, or making a sandwich. It means that the physical setup does not contain usable information that separates them. If there is no possible measurement, even in principle, that could reveal which path was taken, then the alternatives remain indistinguishable. But if some system somewhere carries a path-dependent mark, then the alternatives are distinguishable, even if that mark is never examined. Quantum physics is not about what we happen to know at breakfast. It is about what information is physically present in the world. This is why the phrase in principle appears so often in discussions of the double slit. If the path can be known in principle, interference disappears. That does not mean someone has to actually know it. It means the information has been written into the physical state of something. The universe has a copy of the clue, and once that copy exists, the photon's alternatives no longer interfere as before. It is as if the two possible stories have been separated into different files, and once separated, they can no longer overlap into the same pattern. This also helps explain why the effect is not merely about disturbing the photon. It is tempting to say, well, of course, looking changes things. To see the photon, you must interact with it, and that interaction knocks it around. If you tried to measure a soap bubble with a broom, you would disturb it too. But quantum experiments are subtler than that. There are arrangements where the disturbance can be made very small, yet interference still depends on whether path information exists. The crucial feature is not just a shove or a bump, it is whether the two alternatives become distinguishable. The clue is the key. Think about a detective story again. Suppose a crime could have been committed through one of two doors. If there are no fingerprints, no footprints, no camera footage, and no witness, the two possibilities remain open. In ordinary life, we assume one route still happened, even if no one knows. But in quantum physics, when the alternatives remain unmarked, they do not behave like separate hidden facts. They behave like possibilities that can interfere. Now suppose a single faint footprint appears by one door. Even if nobody studies it yet, the situation has changed. A path record exists. In the quantum experiment, that kind of record changes the possible pattern. Of course, photons are not criminals, though they do often flee the scene at the speed of light. The point is that quantum alternatives are delicate. They can remain coherent only when the world does not keep track of which alternative occurred. Coherence allows interference. Path information destroys that coherence. This process is closely related to decoherence, the way quantum possibilities become entangled with the environment and lose their ability to interfere in any visible way. Decoherence is one reason the world around us looks classical. The environment is constantly collecting information about large objects. Your chair, your blanket, your cup of tea, all of them are being monitored by light, air molecules, heat, and countless tiny interactions. The universe is very nosy at large scales. A photon in a carefully controlled experiment is different. Scientists can isolate it enough that its alternatives remain coherent. They can keep the path unmarked, and the interference pattern appears. Then, by adding a which-way detector, they can let the path information leak into the apparatus. The interference disappears. This ability to switch between wave-like and particle-like behavior by changing the availability of information is what makes the double slit so powerful. It is not just a demonstration that light is strange, it is a demonstration that physical information shapes the result. Now, let us be clear about what is not happening. The photon is not first travelling like a little wave, then noticing a detector, then deciding to become a particle because it feels watched. It is not performing for the audience. It is not embarrassed by surveillance. The photon's behavior is described by the whole experimental context. When the context keeps the paths indistinguishable, the quantum state includes alternatives that interfere. When the context marks the paths, the alternatives become correlated with different detector states. Once that happens, the interference pattern in the ordinary screen data is gone. This idea becomes even more interesting when we consider how tiny the clue can be. Which-way information does not have to be written in a notebook. It can be encoded in the polarization of light, which is a property related to the orientation of its electromagnetic vibration. It can be encoded in the state of another particle. It can be carried by an entangled partner photon. It can be hidden in a detector arrangement where the path is not obvious to a person, but still physically present in the correlations. Quantum physics is not impressed by whether a clue is convenient. If it is enough to distinguish the paths, it matters. Suppose, for example, that each slit changes the photon in a different subtle way. A photon passing through the left slit receives one kind of mark. A photon passing through the right slit receives another. The marks do not have to be large. If the marks are different enough that they could tell the paths apart, interference is reduced or lost. But if those marks are later made indistinguishable again, interference can return, at least in the properly sorted results. That is the basic spirit of the quantum eraser. It asks whether the destruction of interference is truly permanent, or whether it depends on the continued availability of which-way information. The answer is that the availability matters. If the path marks are erased in such a way that no path can be known, then the wave-like interference can be recovered. But the recovery is not always visible in the full unsorted pattern. Often it appears only when the data is separated according to related measurement outcomes. This will become very important when we reach the delayed choice version. The eraser does not create a simple interference pattern on the first screen that someone could use to send a message into the past. It reveals interference in correlations. The pattern is there only when the right events are compared. This is a subtle point, but it keeps the experiment from becoming science fiction. If the later erasing choice could visibly change the earlier screen pattern by itself, then perhaps we could use it to send information backward in time. We could choose erase or do not erase and make the past screen show one pattern or another. But nature does not allow that. The first screen alone shows no usable signal from the future choice. Only after the results are compared with the partner measurements do the hidden interference patterns emerge. Causality remains safe, though perhaps slightly ruffled around the edges. Still, even without time travel, the role of which-way information is startling. It says that the wave-like or particle-like behavior of a photon is not a property the photon carries alone, like a luggage tag. It depends on the relationship between the photon and the rest of the experiment. A path becomes real as a classical fact when the path leaves a distinguishable record. Without such a record, the alternatives do not act like separate facts. They remain part of a combined quantum description. This is the heart of the mystery. The universe does not merely hide information from us. In some cases, the existence or absence of information changes which description applies. There is a quiet difference between not knowing and not being knowable. Not knowing is ordinary. You may not know how many biscuits are left in the tin without checking. The number is still definite, assuming no one in the house is being evasive. Not being knowable in the quantum sense is deeper. If the experiment is arranged so that no physical record distinguishes the paths, then the path is not merely unknown. It is not a definite classical fact in the way we imagine. The photon's alternatives can interfere because they have not been separated into knowable routes. This is where the double slit starts to feel less like an experiment about light and more like an experiment about reality itself. What counts as a fact? When does a possibility become an event? Is a path something the photon always has, or something that becomes meaningful only when the world contains a record of it? These are not easy questions. Different interpretations of quantum mechanics answer them differently. Some say the wave function collapses when measurement occurs. Some say every possible outcome continues in a branching multiverse. Some say quantum states are about information, not hidden objects. Some avoid speaking too much about what is really happening and focus only on what can be predicted. Physicists are very good at calculating the results, and somewhat less united about what the calculations are trying to tell us. But for the quantum eraser, we do not need to settle every interpretation. We need the working facts. When no which-way information exists, interference appears. When which-way information exists, interference disappears. If the information is erased so that the paths become indistinguishable again, interference can be recovered in the right correlations, and if the erasing happens after the photon has already arrived, the experiment seems to challenge the ordinary order of cause and effect, though it does not allow a message to travel backward in time. The tiny clue, then, is not tiny in meaning. It is a small physical mark with enormous consequences, a detector state, a polarization change, an entangled partner, a trace left in the environment. Any of these can be enough to separate the paths. And once the paths are separated, the photon no longer builds the same interference pattern. It is as if the universe is saying, if you want to know which way it went, you cannot also keep the full wave pattern of both ways together. There is a trade. Not because nature is being difficult for amusement, though it sometimes feels that way, but because the mathematical structure of quantum mechanics connects distinguishability and interference at the deepest level. There is something almost poetic in the fact that the smallest clue can silence the wave. A photon passes through a pair of openings. Its possible paths could have overlapped and painted stripes of light and shadow. But a trace appears. A path is marked. The alternatives are separated. The interference fades. The photon becomes part of a more definite story. Not because we forced it with our attention, but because the world kept a record. And now we can begin to see why erasing that record might be so powerful. If the clue is what destroys the interference, then removing the clue might allow the wave-like behavior to return. But what does it mean to remove a clue in quantum physics? Can information really be erased? What if the clue is not held by a simple detector near the slit, but by another photon entangled with the first? What if that other photon travels away and is measured later? What if the first photon has already landed before the fate of the clue is decided? This is where the experiment begins to turn from strange to almost unsettling. Which way information is the hinge? It is the tiny detail that decides whether light behaves as a wave of possibilities or as a set of particle-like arrivals. Once we understand that, the next step is to ask how such information can be shared between particles. Because in the delayed choice quantum eraser, the clue is not simply placed beside the slit like a signpost. It is carried in the relationship between entangled photons, and that relationship will lead us into one of the deepest and quietest connections in quantum physics. To understand the quantum eraser, we now need to meet one of the strangest partnerships in the universe. It is called entanglement, and it is the kind of idea that sounds impossible until experiments keep quietly insisting that it is real. Entanglement happens when two quantum objects become linked so deeply that they cannot be described as completely separate things, even if they travel far apart. They may move in different directions, they may end up in different detectors, they may never meet again, and yet, in the language of quantum physics, they still belong to one shared description, like two notes from the same chord drifting through separate rooms. This is not a normal connection. It is not like two walkie-talkies sending signals. It is not like two people texting across a city, although if photons could text, one imagines the messages would be very short and arrive alarmingly fast. Entanglement is not a hidden radio channel between particles. It is not a tiny thread pulling one particle when the other is touched. It is stranger and more subtle than that. When two particles are entangled, certain properties of the pair are linked before either particle is measured. The result for one particle is not independent of the result for the other, but that does not mean one sends a usable message to the other. It means the pair must be treated as a single quantum system, even when its two parts are separated in space. This was the idea that famously troubled Albert Einstein. He did not like the thought that measuring one particle could be connected to the state of another faraway particle in a way that seemed faster than any ordinary influence should travel. He used the phrase spooky action at a distance, or words very close to that, and one can understand the discomfort. Einstein had helped teach physics that nothing carrying information should travel faster than light. Yet entanglement seemed to create a connection that ignored distance. Not a connection that lets you send a letter faster than light, sadly. That would have made postal services much more interesting. But a connection that shows up in the statistics when the two particles are later compared. To see the basic idea gently, imagine a pair of gloves placed into two sealed boxes. One glove is left-handed, the other is right-handed. If one box is sent to London and the other to Tokyo, then opening the London box and finding the left glove instantly tells you the Tokyo box contains the right glove. But there is nothing mysterious about that. The gloves had definite properties all along. You just did not know which box contained which glove until one was opened. That is ordinary ignorance. It is the kind of uncertainty we live with all the time. The biscuits were either eaten or not eaten before you check the tin, though the answer is usually not the one you hoped for. Entanglement is not like that simple glove story. In quantum experiments, the results cannot be explained as if each particle simply carried a hidden instruction from the beginning, like a tiny note saying, when measured, be left-handed. Experiments have tested this idea again and again. The correlations between entangled particles are stronger and stranger than ordinary hidden instructions allow. Before measurement, the pair is not best described as two separate objects with fixed private properties. It is described as a shared quantum state, one that gives definite correlations when measurements are performed. The pair has a hidden story, but not in the simple sense of a finished script tucked into each particle's pocket. This matters for the quantum eraser because the which-way information does not always sit in a detector near the slits. Sometimes it is carried by an entangled partner. One photon may go toward a screen, while its partner travels elsewhere through a more complicated arrangement of mirrors and detectors. The first photon's pattern alone may look like a jumble, but the partner photon carries information that can help sort the first photon's results later. The two photons share a quantum story, and that shared story is what lets the eraser experiment produce its strange patterns. Let us build the idea slowly. Suppose a photon is sent into a special crystal. Under the right conditions, that crystal can produce two lower energy photons from the original one. These two new photons are entangled. They are born together in a shared quantum state. In many explanations, one photon is called the signal photon, because it goes toward the main detection screen. The other is called the idler photon, because it travels along a different route and is measured separately. Idler is a rather unfair name, as if the second photon is lounging about while the first does all the hard work. In truth, the idler is essential. It carries the clue that helps reveal what kind of pattern is hidden in the data. The signal photon may travel toward a detector that records where it lands. It arrives as a single dot, as photons always do when detected. Dot after dot builds up over time. If you look only at that screen, you do not immediately see the beautiful interference pattern you might expect from the ordinary double slit when no path information exists. The result looks washed out, more like a blend of possibilities. But the signal photon is not alone in the full experiment. Its entangled partner is travelling through another part of the setup, and the way that partner is measured determines whether path information is preserved or erased. Now that sentence is easy to misunderstand. It is tempting to picture the idler photon as sending a command backward to the signal photon. Something like, please behave like a wave now, or sorry, particle mode today. But that is not what happens. The signal photon does not wait on the screen for later instructions. The dot is recorded. The detector clicks. The event happens. What changes later is how that recorded event can be sorted according to the measurement of its entangled partner. The full meaning is not found in the signal photon alone. It is found in the correlation between the two photons. Correlation is a gentle but important word here. Imagine two musicians playing parts of the same duet in separate rooms. If you listen to only one room, the melody may sound incomplete. It may seem wandering, perhaps even random. But if you later bring both recordings together, you hear how the parts fit. The duet was not created by listening later. The later comparison reveals the relationship that was already built into the performance. Entangled photons are not musicians, and quantum measurement is far stranger than a duet, but the basic idea helps. One photon's data alone may not show the pattern. The pattern appears when paired events are compared with the correct partner information. This is why the quantum eraser does not give us a simple machine for changing the past. If the signal screen alone changed depending on a later choice, then perhaps we could send messages backward in time. We could choose to erase or preserve information later and make the earlier screen show a different pattern. But nature does not allow this. The signal screen by itself looks the same no matter what choice is made for the idler. Only after the signal data is sorted using the idler results do the interference patterns appear or disappear. The strangeness is real, but it is locked inside correlations. The universe lets us discover the pattern, not use it as a cosmic telephone to yesterday. Still, the correlations are not ordinary. Entangled photons force us to give up the idea that each photon always carries its own separate classical story. In the quantum eraser, the signal photon's possible paths and the idler photon's later measurement are part of one shared arrangement. Which way information may exist in the joint state of the pair. If the idler's path can reveal which route the signal photon was associated with, then interference is lost in the relevant data. If the idler is measured in a way that erases that route information, then interference can be recovered in the sorted signal results. The pair behaves as a connected system, not as two fully independent travellers. This is where the hidden story becomes so important. The signal photon's journey is not complete in the classical sense until we consider its relationship with the idler. A dot on the screen is a real event, but what kind of pattern that dot belongs to depends on the shared information structure. Is it part of a group where which way information is preserved? Then it contributes to a particle-like distribution. Is it part of a group where which way information has been erased? Then it may contribute to an interference pattern. The dot itself does not move, it is not rearranged. It is not corrected after the fact with a tiny quantum eraser rubbing at the screen. Its meaning within the data depends on how it is correlated. That may sound less dramatic than rewriting the past, but in some ways it is more profound. It suggests that the past of a quantum system is not always a simple chain of definite events waiting to be read. The past may depend on the total measurement context. When we ask which path did the photon take, the answer may only make sense if the experiment contains information that distinguishes the paths. Without that information, the photon's history may not be a single classical route. With entanglement, the question becomes even more delicate, because the relevant information may not be located with the photon we first detect. It may be spread across the shared state of two photons. Entanglement also helps us understand why the eraser can be delayed. The idler photon can be sent along a longer path than the signal photon. This means the signal photon may hit its detector first. Its position is recorded before the idler is measured. Later, the idler reaches its own detectors, where the experiment either preserves or erases path information. When the results are later compared, the signal photon detections can be sorted into different groups. Some groups show interference, others show a complementary pattern, others show no interference because which way information remained available. The timing is what makes the experiment feel almost unreal. The signal photon seems to have landed before the choice about the path information was settled, but the safer way to say it is that the full entangled system is not described by the order of events in the ordinary classical story we prefer. The signal detection and the idler detection are linked in the joint quantum description. The later measurement does not send a message back to the earlier detection. Instead, it determines which subset of the already recorded signal events we are looking at when we compare the data. The apparent backward influence is not a controllable influence. It is a pattern revealed through entanglement. This distinction matters because without it, the quantum eraser becomes too easy to turn into myth. It is often described as if a photon decides whether it went through one slit or both after it has already arrived. That is a striking phrase, but it is not quite careful enough. The experiment does challenge our ordinary idea of a fixed path. It does challenge the idea that the photon must have had a classical route all along, but it does not show that human choices magically rewrite history. It shows that quantum histories are not always classical histories. They are tied to what information exists and how the system is measured. Let us pause with that for a moment. In ordinary life, the history of an object feels independent of later questions. A raindrop falls on a window. Later, you may look at the streak it left behind. Your looking does not decide whether the raindrop fell on the left side or the right side. A bicycle passes through a gate. Later, you may check a muddy tyre track. The bicycle had a path whether or not you check. This is the classical picture, and it works beautifully for everyday things. But a photon in a carefully protected quantum experiment is not leaving a fully classical trail unless the experiment creates one. Its possible paths are not the same kind of facts as a bicycle's tyre marks. Entanglement makes this even stranger because the trail can be stored in another particle. The idler photon can carry information that, if measured one way, tells which path information. If measured another way, it removes the ability to tell the paths apart. This signal photon's detection record then falls into different meaningful patterns depending on the idler outcome. It is as if the clue to the first photon's story is written in a second photon's notebook, and the notebook can be read in ways that either reveal the route or make the route unknowable. Again, not a perfect image, but it gives the right feeling. The story is shared. The word shared is crucial. Entangled photons are not like two separate coins tossed in different rooms. They are more like a single quantum event with two distant outcomes. Each detection is local and definite. One detector clicks here, another clicks there. But the relationship between those clicks is not something we can explain by treating the photons as fully separate ordinary objects from the start. The pair has a structure that only becomes visible in repeated experiments and later comparison. One pair gives one pair of results. Many pairs reveal the pattern. This is why quantum physics is so patient. It rarely tells its deepest truths in a single event. One photon dot looks random. One detector click looks modest. One pair of entangled measurements looks like a coincidence. But repeat the experiment many times, gather the data carefully, compare the pairs, and a hidden order appears. The universe whispers in statistics. It does not always shout in single moments. This is inconvenient for anyone hoping for a dramatic lightning bolt of understanding, but very fitting for sleepy science. Quantum truth arrives dot by dot, click by click, like rain slowly drawing a pattern on glass. Entanglement has been tested in many ways beyond the quantum eraser. Experiments inspired by the work of John Bell showed that the world cannot be explained by simple local hidden variables of the old classical kind. In plainer words, entangled particles do not behave as if they merely carried pre-written instructions that were fixed before measurement and unaffected by the choice of measurement settings. The correlations are too strong. Nature seems to preserve a kind of unity across separated systems that classical imagination cannot easily picture. At the same time, these correlations cannot be used to send faster than light messages. Relativity remains protected. The universe allows deep connection, but not cosmic cheating. That balance is one of the most beautiful and frustrating features of quantum physics. Entanglement is real, but it cannot be used like a magical signal. The quantum eraser is strange, but it does not allow time travel communication. Measurement choices matter, but not in the simple way our everyday minds expect. The universe seems to walk a narrow path between mystery and order. It gives us results that are deeply surprising, yet never sloppy. The rules are exact. The predictions are precise. The interpretation is what keeps everyone awake, which is why we will treat it gently. For the delayed choice quantum eraser, entanglement supplies the hidden bridge. Without entanglement, the first photon's dot on the screen would simply be one more detection. With entanglement, that dot belongs to a pair. Its partner carries information that can decide how the dot is later classified. The signal photon and idler photon share a story, and that story can be read in different ways. If the idler measurement preserves which-way information, the signal events align with particle-like behavior. If the idler measurement erases which-way information, the signal events can be sorted into interference patterns. The strange part is that this can be arranged even when the idler is measured after the signal has already landed. So the hidden story is not hidden in the sense of a secret classical path waiting behind the curtain. It is hidden in the correlations of the entangled state. The meaning of one result cannot be fully separated from the other. To ask what happened to the signal photon alone may be to ask an incomplete question. The complete question involves the pair, the measurement choices, and the information that remains available. This is a very different picture from the one we use for stones, doors, and falling apples, but it is the picture nature gives us when we deal with light at its most delicate level. There is a quiet lesson here about separateness. In everyday life, we divide the world into individual things. This cup, that chair, this person, that lamp. The divisions work well enough, and without them breakfast would be very confusing. But quantum entanglement tells us that the deepest description of small systems may not always respect our preferred boundaries. Two photons can be separated in space and still belong to one quantum whole. Their properties may not be fully individual until measured. Their shared state can hold information that no single part carries alone. Reality, at least in this tiny domain, is not always built from separate pieces first and relationships second. Sometimes the relationship comes first, and that is exactly why the quantum eraser feels so close to the edge of ordinary thought. We are used to believing that events happen, then information about them may or may not be discovered. But entanglement suggests that what counts as an event, what counts as a path, and what counts as a history may depend on the wider quantum relationship. The signal photon and idler photon do not merely have two private stories that we later compare. They have one shared story that becomes readable only through measurement. As we move from entanglement toward the delayed choice itself, the stage is now nearly set. We have the double slit, where wave-like interference appears when paths are unknowable. We have which-way information, the tiny clue that destroys interference by separating the alternatives. Now we have entanglement, the strange link that allows that clue to be carried by another photon, measured elsewhere, and sometimes measured later. The next turn is the one that makes the mind lean forward. What happens when the signal photon has already arrived, its dot already recorded, while its entangled partner has not yet revealed whether the path information will be kept or erased? The phrase delayed choice sounds almost too dramatic for something that happens in a laboratory. It suggests a universe caught off guard, as if nature has already begun writing one story, and then, rather late in the sentence, someone changes the ending. A photon has flown, a detector has clicked, a tiny dot has appeared where it appeared. Then, only after that arrival, the experiment seems to decide whether the photon behaved like a wave or like a particle. It is the kind of situation that makes common sense sit down slowly and ask for a very strong cup of tea. But delayed choice did not begin as a magic trick. It began as a careful question. What if the decision about how to measure a quantum object is made after the object has already entered the experiment? What if, instead of setting up the apparatus in advance to ask whether light behaves as a wave or a particle, we wait until the last possible moment? Would the photon already have committed to one behavior? Would it have travelled like a wave if both paths were open and unmarked, or like a particle if the route could be known? Or is that whole way of speaking just our classical imagination trying to force a tiny quantum event into a human-sized story? This question was strongly associated with the physicist John Wheeler, who loved experiments that pushed reality into awkward corners. Wheeler imagined versions of the double-slit experiment where the choice of what to measure could be delayed until after the photon had already passed the slits. The basic idea was simple in spirit, though subtle in practice. If you arrange the experiment one way, you can reveal wave-like interference. Arrange it another way, and you can reveal particle-like path behavior. But what if the photon is already on its way before you decide which arrangement it will meet? Does it travel through the experiment knowing in advance what you will later ask? Does it change its past behaviour? Or is the photon not the kind of thing that has a definite wave or particle identity before the measurement context is completed? Wheeler's delayed choice idea was not originally the same as the quantum eraser, but it prepared the ground for it. It said, in effect, let us not assume the photon carries a finished story through the apparatus. Let us test whether the story depends on the whole experimental arrangement, even when part of that arrangement is decided later. The result is not that the photon receives a message from the future in the ordinary sense. It is not a little light particle glancing at tomorrow's schedule and adjusting its behaviour accordingly. The deeper lesson is more unsettling and more precise. Quantum objects may not possess the definite classical properties we imagine until the conditions of measurement define what can be said. In everyday life, delayed choice would make no sense at all. Suppose you are walking through a train station with two exits. You choose the left exit, buy a coffee, and continue on your way. 10 minutes later, someone decides whether to look at the security camera or not. Their later decision does not change which exit you used. You used the left exit. There was a definite path. Your coffee may have been regrettable, but the path was not. The later measurement simply reveals or ignores a fact that was already there. Classical history does not wait for permission to become history. With a photon, the situation is not so easily described. In the double-slit experiment, if there is no which-way information, the photon's possible paths can interfere. If there is which-way information, interference disappears. The problem is that we are tempted to say the photon must have been travelling either as a wave or as a particle all along, long before the measurement. Delayed choice challenges that temptation. If the measurement arrangement is chosen after the photon has entered, or even after it has passed the crucial region, then it becomes harder to believe the photon simply carried one fixed identity through the experiment. Think of it like asking a question after the answer should already have been written. If the question is, which path did you take? The photon can be made to give a particle-like answer. If the question is, did the alternatives interfere? It can reveal wave-like behaviour. But in delayed choice, the decision about which question will be asked comes late. That lateness is what makes the experiment feel as if the photon's earlier behaviour is being selected after the fact. But perhaps the real mistake is believing there was a simple earlier behaviour of the classical kind waiting to be selected. This is the quiet shift quantum physics asks of us. Instead of picturing the photon as a tiny traveller that must secretly know whether it is a wave or particle, we picture it as a quantum system described by possibilities. Those possibilities evolve through the experiment. The final measurement does not merely uncover a classical secret. It defines which aspect of the quantum system becomes visible. The choice can be delayed because the photon was not carrying the kind of finished classical record our intuition expects. It was carrying a quantum possibility structure, and the measurement determines how that structure is expressed. Now, that may sound like a clever way of avoiding the spooky conclusion, but it is not an evasion. It is exactly the point. Delayed choice experiments are not strange because they show the future physically pushing the past around like furniture. They are strange because they undermine the assumption that the past of a quantum object must be made from definite little facts in the same way as the past of a chair, a train ticket, or an accidentally overwatered houseplant. The photon's history is not necessarily a classical path waiting behind the curtain. It is tied to the measurement that makes path or interference meaningful. The delayed choice quantum eraser adds one more layer. Here, the photon we watch is part of an entangled pair. One photon, often called the signal photon, travels toward a detector where its position is recorded. The other photon, the idler photon, travels along a separate route toward a set of detectors that handle the which-way information. The experiment can be arranged so that the signal photon arrives first. It has already landed. Its dot is already written into the record. Then, later, the idler photon is measured in a way that either preserves which-way information or erases it. This is where the mind naturally rebels. How can a later measurement of the idler photon affect whether the earlier signal photon behaves as part of an interference pattern? The signal photon already landed. The detector already clicked. The dot is not waiting in a state of polite uncertainty on the screen, asking whether it should move slightly to the left in case someone chooses the eraser. Nothing visible changes on the screen after the fact. The dot remains where it was. No tiny hand reaches out from the future to rearrange the result. And yet, when many such paired events are compared later, the signal-photon detections fall into different patterns depending on how the idler photon was measured. The key is that the pattern is not visible in the signal detections alone. If you look only at the screen where the signal photons land, you see a distribution that does not let you know which later choice was made for the idler photons. There is no message from the future. There is no usable signal. But when scientists compare each signal photon with its entangled idler partner and sort the data according to the idler result, hidden patterns appear. In the groups where the idler measurement erased which-way information, the signal photons show interference-like behavior. In the groups where the idler measurement preserved which-way information, they do not. This sorting is not a trick in the dishonest sense. It is not cherry-picking random dots until a nice pattern appears, like finding shapes in clouds and declaring one of them to be your uncle. It is a precise comparison between entangled pairs. Each signal photon has a partner. Each partner reaches one of the idler detectors. The idler result tells scientists which subset of signal detections belongs together. Once the data is divided according to those outcomes, the quantum correlations reveal themselves. The interference is not drawn by moving dots. It is revealed by sorting the already recorded dots through the shared story of the entangled pair. That is why the delayed choice part can feel both extraordinary and carefully limited. The extraordinary part is that the idler measurement can happen after the signal photon has already been detected, yet the correlations still sort into wave-like and particle-like patterns. The limited part is that no one can control the earlier signal screen by choosing what to do later. Without comparing the idler results, the signal screen alone contains no usable information about the later choice. The universe allows a pattern that seems to cross our ordinary sense of time, but it hides that pattern inside correlations that can only be uncovered afterward. Reality is being strange, but not reckless. Let us slow that down. Suppose a signal photon lands at a detector first. It makes one mark. Later, its idler partner reaches a detector that tells us which way information was preserved. That signal mark is placed into a group that shows no interference. Another signal photon lands. Later, its idler partner reaches a detector that erases which way information. That signal mark is placed into a group that contributes to an interference pattern. The marks were all already there. The later idler results do not rewrite the marks. They determine how the marks can be meaningfully grouped. The appearance of delayed influence comes from the fact that the grouping depends on a measurement performed later. This is still unsettling because in ordinary life the category of an event usually feels settled when the event happens. If a coin lands heads, it is heads. If a letter enters one mailbox, it entered that mailbox. Later sorting may help us organize records, but it does not decide what kind of event occurred. In the quantum eraser, the category wave-like or particle-like is not attached to the signal detection alone. It belongs to the relation between the signal detection and the idler measurement. The event's place in a pattern depends on the entangled pair as a whole. That is why delayed choice makes the past seem flexible. The past event is fixed as a dot, but its quantum meaning is relational. Relational is not a word that usually appears in bedtime thoughts, unless one has had a particularly complicated family dinner, but it is useful here. Quantum physics often suggests that properties are not always private possessions of single objects. They can be features of relationships between systems. The signal photon's dot is real. The idler detector's click is real. But whether a particular collection of signal dots reveals interference depends on their relationship to idler clicks. The property does not live entirely in one photon by itself. It lives in the pattern connecting both. This is where delayed choice begins to challenge our idea of the past. We usually imagine the past as a row of completed facts, each one tucked neatly behind us. A photon passed through the left slit. A photon passed through the right slit. A photon behaved like a wave. A photon behaved like a particle. But the delayed choice quantum eraser suggests that these statements may not be valid unless the experiment contains the information needed to support them. If which way information is preserved, it makes sense to talk about paths. If it is erased, the path distinction no longer belongs to the pattern we observe. The past is not rewritten in the sense of changing a fact. Rather, the kind of fact we are allowed to claim depends on the full measurement context. That may sound like wordplay, but it is not. It is a crucial difference. To say the past was changed implies there was a definite classical past first, then something later reached back and altered it. Quantum physics may be telling us something subtler. The photon did not necessarily have the kind of definite path we imagine before the measurement structure made that path meaningful. So the delayed choice does not change a finished path. It reveals that the idea of a finished path may have been the wrong idea from the beginning. This is why Wheeler once described the universe in terms of participatory reality. Not participation in the mystical sense of human thoughts creating mountains or stars. Mountains and stars are doing quite well without our opinions. But in the quantum sense, that measurement is part of what defines the observable properties of a system. The questions we arrange physically shape the answers that can appear. Delayed choice makes this especially vivid because the question can be arranged late, after we would normally assume the answer was already settled. There is a calm but enormous difference between saying measurement creates reality from nothing, and saying measurement defines which physical property becomes definite. The first is too broad and misleading. The second is closer to the heart of quantum mechanics. A photon is not a blank nothing before detection. It has a quantum state. It evolves according to reliable rules, but that state does not assign all the classical properties we might want at once. We cannot always ask it to have both a definite path and full interference. The experimental context chooses which kind of information becomes part of the world's record. Delayed choice experiments show this with particular elegance. If the apparatus asks for interference, wave-like behavior appears. If it asks for path information, particle-like behavior appears. If the choice is made late, the result still follows the question asked. The photon does not seem to carry a predetermined classical answer independent of the measurement. It gives the answer appropriate to the final arrangement. Again, this does not mean a person's free will sends a command into the past. It means the quantum description is not complete in classical terms until the measurement context is completed. There is a lovely discomfort in that phrase, final arrangement. In the everyday world, we assume what happened should not depend on how we later arrange our questions. But quantum experiments are not simply about uncovering a hidden diary. They are about creating physical conditions under which certain alternatives can or cannot interfere. If the path alternatives remain indistinguishable, interference belongs to the results. If the alternatives are marked, interference is lost. If the marking is erased, interference can be recovered in correlations. The delayed choice only sharpens the point by making the timing awkward for our intuition. The timing, however, does not break relativity. This is important. Although the correlations can appear astonishing, they cannot be used to send a faster-than-light signal or a message backward in time. The signal photon detections alone do not reveal the later idler choices. Only when the records from both sides are brought together by ordinary communication do the patterns become visible. That ordinary communication cannot outrun light, so the deeper laws remain consistent. The universe seems willing to unsettle our picture of what a photon's past means, but not willing to let us send tomorrow's lottery numbers to yesterday, which many people would consider a missed opportunity. Still, Even without usable time travel, delayed choice remains one of the sharpest demonstrations that quantum reality is not simply classical reality with smaller parts. It tells us that the story we tell about a quantum event depends on the whole arrangement, including measurements that may happen later in the laboratory timeline. The signal photon's arrival is not enough by itself to decide whether it belongs to an interference pattern. Its entangled partner's later measurement is part of the full story. This does not change the dot. It changes the context in which the dot becomes meaningful. A useful image is a photograph found in a box but with no label. By itself, it shows a face in a crowd. Later, you find a notebook explaining that the photograph belongs to one of several different albums. When you place it in one album, it becomes part of a wedding, in another part of a political rally, in another part of a film set. The photograph itself did not change, but the story it belongs to depends on the later information connecting it to a larger context. The quantum case is deeper and more mathematical than that, of course, but the image helps soften the shock. A single event can be real and still not tell its full story alone. The delayed choice quantum eraser uses that kind of incompleteness at the smallest scale. The signal photon's detection is real, but not self-explanatory. Its partner photon carries the information needed to place it in the correct pattern. When the partner is measured in a way that preserves path information, the story becomes particle-like. When the partner is measured in a way that erases path information, the story becomes wave-like. If the partner is measured later, then the story appears to be completed after the signal photon has arrived. But perhaps it is better to say the story was never a simple single photon story. It was always a two-photon quantum story. This is why the delayed choice is so important for the quantum eraser. It prevents us from saying that the photon must have known in advance whether which way information would be erased. It prevents us from imagining a simple path chosen at the slits and merely revealed later. The timing forces us to confront the fact that quantum descriptions do not fit neatly into the order of ordinary narratives. We want beginning, middle, and end. Quantum mechanics gives us preparation, evolution, measurement, and correlations. It is a story, but not one written in the grammar of everyday objects. There is something almost humbling about this. A photon is not large. It does not fill a room. It does not thunder or burn or announce itself with cosmic importance. And yet, in its quiet arrival at a detector, it reveals that the world may not be built from definite histories in the way we imagined. It shows us that information is not merely a human convenience. It is woven into the physical behavior of light. A decision made after arrival can decide how earlier detection events are sorted into patterns, because the relevant reality is not just the first photon alone, but the entangled structure connecting it to another. As we move closer to the eraser itself, the question becomes sharper. If which way information destroys interference, and if entanglement can carry that information away into another photon, then what happens when the later measurement of that other photon removes the path clue completely, not just hides it from a person, not just misplaces it in a drawer, but makes the alternatives genuinely indistinguishable in the measurement? That is the erasing step, the move, that gives the experiment its name. And once that step is added, the delayed choice becomes even stranger, because the wave pattern can be recovered from events that seemed, at first, to have already chosen another story. Now the clue has been placed, and the photon has become part of a more complicated story. We have seen that when the path is unknowable, light can build an interference pattern, as if its possible routes remain open and able to overlap. We have seen that when which-way information exists, even as a tiny physical trace, that interference fades away. The photon no longer behaves as though the two paths are blended. The alternatives have been marked apart. The universe has kept a note. And in quantum physics, even a very small note can be enough to change the entire pattern. The quantum eraser asks a question that seems almost too clever for its own good. If the clue is what destroys the interference, what happens if we remove the clue? Not ignore it. Not close our eyes and pretend it was never there. which is a strategy many of us have tried with laundry. Not simply lose the notebook in a drawer and hope for the best, but physically arrange the experiment so that the path information is no longer available, even in principle. If the universe can no longer tell which way the photon went, can the wave pattern return? Astonishingly, the answer is yes, though with some very important care. The interference can be recovered, but not always as a simple pattern appearing directly on one screen. Often it appears only when the recorded events are sorted according to the outcomes of another measurement. This is where the quantum eraser becomes both beautiful and easily misunderstood. It does not show a screen magically changing after the fact. It does not show dots sliding into new positions like shy insects rearranging themselves under a microscope. It shows that the wave-like pattern was hidden in the correlations, and that when the path clue is erased, the correct sorting reveals the interference that seemed to be lost. To make sense of this, imagine the simplest idea first. A photon approaches a double-slit arrangement. The two paths are possible. If nothing marks them, interference can appear. But now suppose we add a way of marking the paths. Maybe a photon passing through one slit receives one kind of tag, and a photon passing through the other slit receives another kind of tag. The tags are not labels written in ink. They are physical differences in the quantum state, differences that could allow someone or some detector to determine which path was taken. Once those tags exist, the paths are distinguishable, the interference disappears. Now comes the eraser. Instead of measuring the tags in a way that reveals the path, we measure them in a different way, one that makes the two path tags indistinguishable. The route information is no longer available. The experiment no longer contains a usable answer to the question, which way did the photon go? And when that happens, the interference can be restored in the appropriate data. It is as if the photon's wave-like behavior had not been destroyed by a rough shove, but hidden by the existence of a clue. Remove the clue, and the wave can be seen again. This is why the word eraser is both useful and dangerous. It is useful because it captures the idea that path information can be removed. It is dangerous because it makes us imagine something too simple. We might picture a piece of information written down, then rubbed away. But quantum erasing is not like wiping chalk from a board. It is not deleting a file from a cosmic computer. It is arranging a measurement so that two alternatives become physically indistinguishable again. The information is not merely forgotten by a human being. It becomes unavailable in the structure of the experiment. This distinction matters. Suppose you know which slit the photon went through, then you decide not to tell anyone. That is not a quantum eraser. The information still exists in your memory, and your memory is a physical state of your brain. The universe still has the clue, even if you are being secretive. Suppose a detector records the path, then you turn off the screen before looking. That is not enough either. If the detector still holds the record, the path information has to be erased in the physical quantum sense. The alternatives must no longer be distinguishable by any measurement of the relevant system. It is not ignorance that restores interference. It is indistinguishability. This is one of the quietest but deepest points in the whole subject. Quantum physics does not care whether we personally happen to know something. It cares whether the information exists physically. If the path is knowable in principle, the interference is gone. If the path is not knowable, because the physical clues have been erased, then interference can return. The difference between not looking and not being able to know is enormous. In everyday life, not looking is often enough to preserve mystery. In quantum physics, the universe is less easily fooled. It has to be genuinely unable to tell the paths apart. Now let us bring entanglement back into the picture. In the delayed choice quantum eraser, the path clue is not simply attached to the same photon that lands on the main detector. Instead, the clue is carried by an entangled partner. A photon is produced as part of a pair. One member of the pair, the signal photon, travels toward the detector where its position is recorded. The other member, the idler photon, travels through another part of the apparatus. Because the two photons are entangled, the idler can carry information related to the path of the signal photon. The clue to one photon story is stored in the shared story of the pair. This arrangement allows something wonderfully strange. The signal photon can land first. It makes its dot. The event is already recorded. Later, the idler photon reaches a set of detectors. Depending on which detector it reaches, the measurement either preserves which way information or erases it. If the idler measurement preserves the path clue, then the corresponding signal photon belongs to a group that does not show interference. If the idler measurement erases the path clue, then the corresponding signal photon belongs to a group that does show interference. The signal dot itself is never moved. The earlier event is not edited, but its place in the pattern depends on how it is connected to the later idler result. This is the part that makes the quantum eraser feel as though it is reaching backward in time. The signal photon has already arrived. The dot is already there. Then the later measurement of the idler photon seems to decide whether that earlier dot belongs to a wave-like pattern or a particle-like pattern. It is tempting to say that the future has rewritten the past. It is tempting, and it is also too simple. The better statement is that the past event alone did not contain the full classical story we wanted to assign to it. Its quantum meaning depends on the full entangled measurement context. Let us picture the data gently. Imagine that many signal photons land on the main detector one after another. If you look at all the dots together, you do not see a clean interference pattern. You see a broad distribution, a mixture. Nothing in that screen alone tells you whether the idler photons were later measured in a path-preserving way or a path-erasing way. This is crucial. If the main screen alone changed according to a later choice, then we could send messages backward in time. We could choose one setting later and make the earlier screen show one pattern, choose another and make it show another. But that never happens. The screen alone remains mute about the future. The hidden structure appears only when the signal dots are matched with their idler partners. Each signal photon belongs to a pair. Each idler photon has its own detector outcome. When researchers sort the signal dots according to those idler outcomes, different patterns emerge. Some sorted groups reveal interference. Other sorted groups reveal a complementary interference pattern, shifted in such a way that when they're added together, they cancel out into the unremarkable mixture seen on the main screen. Other groups may show path-like behaviour, where which way information remained available. The pattern was not visible in the whole pile because different hidden patterns were layered together. An ordinary comparison may help. Imagine you have a box full of transparent sheets. Each sheet has part of a pattern printed on it. Some sheets have stripes aligned one way. Others have stripes shifted the opposite way. If you stack all the sheets randomly, the stripes blur together and disappear. But if you sort the sheets into the right groups, the patterns become clear. The sorting does not create ink on the sheets after the fact. It reveals structure that was hidden in the mixture. The quantum eraser is not exactly a stack of transparent sheets, but the basic feeling is similar. The interference is not produced by moving old dots. It is uncovered by sorting correlated events. This is why the quantum eraser is not a magic trick, and also why it is not ordinary. It does not cheat causality. It does not send a signal into the past, but it does show that the wave-like or particle-like story belongs to correlations, not to a single photon carrying a complete classical identity. The signal photon and idler photon share a quantum state. The idler outcome tells us which kind of information was available in the joint system. When the path information is erased, the signal photons in that subset reveal wave-like interference. When the path information remains, they do not. The phrase restoring the wave can be misleading if we imagine the photon physically turning back into a wave after it has landed. That is not what is happening. The signal photon is already detected as a dot. What is restored is the ability to observe wave-like interference in the pattern of many correlated detections. The wave was never a visible smear on the screen. It was a structure of probability, a set of relationships among possible outcomes. The eraser restores the conditions under which those relationships can show themselves. This tells us something important about what measurement does. When which way information exists, the two path alternatives become distinguishable. They stop interfering. But if the information is erased before it becomes a permanent distinguishable record, the alternatives can become indistinguishable again. Then the interference can appear in the right measurement basis, which in more ordinary words means the experiment is asking the photon pair a different kind of question. Instead of asking which path was taken, it asks a question that mixes the path alternatives together. When the question is asked this way, the answer does not reveal a path, it reveals interference. That is a strange idea, because we usually think every question has one hidden answer waiting behind it. Did the photon go left or right? Surely the answer must be one or the other, but quantum mechanics says that not all classical questions have definite answers in every experimental context. If we set up the apparatus to reveal a path, we get path information and lose interference. If we set it up to erase the path distinction, we recover interference and cannot know the path. The two kinds of knowledge exclude each other, not because of technical clumsiness, but because of the structure of quantum reality. This is closely related to complementarity, the idea that certain properties cannot be fully revealed at the same time. Wave-like interference and particle-like path information are complementary. The more clearly one exists, the less clearly the other can appear. It is not just a problem with our tools. It is not that we need a better camera, a quieter detector, or a physicist with steadier hands. The limitation is built into nature. If the path is marked, the wave pattern is lost. If the wave pattern is restored, the path is no longer knowable. Light will give us one kind of answer or the other, but not both in full. This can feel like nature being evasive, but perhaps it is more accurate to say that our categories are incomplete. We want the photon to be a tiny object with a definite route, and also a wave that interferes with itself. We want to keep the comforting path and the strange pattern at the same time. Quantum mechanics says we cannot. The photon is not a small classical traveller with wave decorations. It is a quantum object whose behaviour depends on the whole measurement arrangement. The eraser does not force the photon to be mysterious. It reveals that the mystery was always there, hidden by the way we ask the question. There is also a quiet lesson about records. A record makes a history more definite. If the path leaves a trace, we can talk about which way the photon went. But if the trace is erased in the right way, that path history is no longer available. The experiment does not then mean the photon definitely went both ways like a little glowing ghost. It means the question, which way, is no longer part of the recoverable physical story. The interference pattern belongs to a situation where the alternatives remained, or were made again, indistinguishable. This is where the quantum eraser becomes unsettling in a very particular way. It suggests that the past of a quantum system is not always a fixed chain of classical facts. A photon's path may not be something that exists independently of the measurement context. If the path is recorded, the past can be described in path terms. If the path information is erased, the same earlier detection can belong to an interference pattern in which path terms are not appropriate. The past is not being rewritten like a sentence corrected with a pen. Rather, the past was never a simple sentence until the experiment determined which language could be used. Let that settle for a moment. The photon lands. That much is definite. A detector records a position. But the story we tell about how that photon came to be part of the final data depends on information. If the information separates the roots, the story becomes particle-like. If the information is erased, the wave-like correlations return. This is not because human attention is magical. It is because information is physical. A path clue is a physical correlation. Erasing the clue is a physical change in what can be distinguished. The universe is not responding to curiosity as a feeling. It is responding to the structure of records. It is helpful to remember that erasing does not mean destroying all information in the ordinary sense. In real experiments, information can be transformed, mixed, or measured in a way that no longer reveals the original path. The important thing is whether the final measurement allows the path alternatives to be told apart. If it does, no interference in that subset. If it does not, interference can appear. The eraser is less like burning a secret document and more like changing the question, so the secret is no longer encoded in the answer. The path clue becomes unavailable, and the alternatives can once again behave as a coherent pair. The delayed version makes the eraser feel sharper, because the erasing choice can be made after the signal photon's position is already registered. This timing makes us want to imagine a cause travelling backward, but the experiment is better understood through the full set of correlations. The signal photon's detection and the idler photon's detection are parts of one entangled system. The later idler result does not alter the earlier signal event. It determines which correlation pattern that event belongs to. The wave is restored not by changing the past dot, but by revealing that the dot participates in a pattern where which way information has been erased. There is a quiet fairness to the universe here. You may erase the which way clue and recover interference, but you cannot also keep the path. You may preserve the path and lose interference, but you cannot have the full wave pattern. Nature does not allow both prize boxes at once. It is rather like being offered either a map of the route or the beautiful pattern made when all possible routes overlap, but not both. If you insist on the map, the pattern fades. If you want the pattern, the map must disappear. The quantum eraser therefore shows us that interference is not destroyed by the mere passage of time, or by the photon landing, or by someone becoming confused, though confusion is certainly common in this subject. Interference is destroyed by distinguishability. Remove the distinguishability and the interference can be recovered. The clue is what matters. The path record is the hinge. The eraser turns that hinge back, not by undoing an event, but by undoing the availability of the path distinction. This is why the experiment has such a powerful place in discussions of quantum reality. It forces us to separate two ideas that everyday life blends together. One idea is that an event has happened. The signal photon landed. That event is real. The other idea is that the event has a definite classical history of the sort we imagine. The photon went through this slit, or that slit. Quantum physics tells us that the first idea can be true, while the second is not always meaningful. A detection can be definite even when the path history is not. The eraser makes that difference visible, and it does so with light, the most familiar and yet deeply unfamiliar thing. The glow beside your bed, the pale wash of moonlight through curtains, the soft shimmer of a screen. All of it is made of quantum objects that behave according to these strange rules. We do not notice because the everyday world is full of records. Light scatters, objects interact, information leaks into the environment constantly. The wave possibilities of large things are drowned in a sea of tiny clues, but in a careful laboratory, with a photon pair and a delicate arrangement of detectors, the hidden quantum grammar can still be heard. The quantum eraser whispers that reality is not only about things moving through space, it is also about what can be known, what is marked, what is distinguishable, and what relationships remain coherent. A photon's wave-like pattern can vanish when the world learns which way it went. The pattern can return when that knowledge is erased, and if the erasing happens after the signal photon has arrived, the result seems to place pressure on our whole idea of before and after. Yet the important calm center remains. Nothing travels back to rearrange the screen. No human mind summons an outcome. No message is sent into yesterday. The experiment is stranger than all that, and more disciplined. It shows that quantum events do not always carry complete classical histories. It shows that information and measurement are not side notes to reality, but part of how reality becomes definite. The wave is restored when the clue is removed because the difference between the paths has stopped being a physical fact the experiment can use, and now the question waiting for us becomes unavoidable. If erasing the which way clue after a photon has already landed can reveal an interference pattern in the sorted data, what should we really say about the photon's past? Did it first behave like a particle, then later become part of a wave story? Did it travel both ways until a path was known? Did it have no definite route at all? Or are all these ordinary phrases simply too clumsy for the quantum world? The eraser does not give us an easy answer, but it leads us straight into the deepest confusion of all, the question of whether the experiment truly rewrites the past, or whether it teaches us that the past was never quite the fixed classical record we imagined. At this point in the story, the question becomes almost impossible to avoid. The signal photon has already landed. Its tiny mark is already sitting in the data. Later, the idler photon is measured in a way that either preserves the clue or erases it. Then, when the records are compared, some of those earlier signal photons belong to a pattern that looks wave-like, and others belong to a pattern that looks particle-like. So it is very natural to ask the unsettling question: did the later measurement change what the photon had already done? Did the quantum eraser reach backward through time and rewrite the past? It is a tempting picture, a wonderfully strange picture too. One can almost imagine the photon arriving at the detector, leaving its little dot, and then waiting politely for a decision from the future. Later, the idler photon reaches its own detector, and depending on what happens there, the signal photon checks its notes and decides whether it had travelled like a wave or a particle all along. This would make the universe sound like a slightly disorganised author editing an earlier page after already sending the manuscript to print. Interesting, yes, but probably not the right way to understand the experiment. The careful answer is that the Dudley's choice quantum eraser does not rewrite the past in the ordinary sense. It does not allow anyone to change a recorded event. It does not let a later choice move a dot that has already appeared. It does not let a scientist send a message backward in time, warn their past self not to eat the suspicious sandwich, or gently suggest buying a different pair of shoes. The earlier detection remains exactly where it was. The data on the signal side alone never changes depending on what is done later. In that very important sense, the past is not edited. But that careful answer is not the same as saying nothing strange is happening. Something very strange is happening. The experiment challenges the idea that the photon's past must have been a simple classical story before it was measured. It suggests that asking what really happened may not always have the kind of answer we expect. The past is not rewritten like a sentence being crossed out. Rather, the past of a quantum object may not have been written in the classical language we keep trying to read from it. In everyday life, when we ask about the past, we assume there is one definite story. If a spoon falls from a table, it followed some path to the floor. If nobody watched it fall, the path still happened. If a camera later reveals the path, the camera did not create it. It only recorded it. A spoon does not wait for a future observer to decide whether it fell on the left side of the table or the right side. It is a spoon. It has no time for such theatrical behaviour. It falls, it clatters, someone sighs, and the matter is settled. Photons do not behave like spoons. That is perhaps one of the most useful sentences in all of quantum physics. Tiny quantum systems do not always carry definite classical properties in the way large objects appear to. In the double-slit experiment, a photon does not simply travel through one slit while secretly hiding that fact from us. If the path is unmarked, the alternatives can interfere. If the path is marked, interference disappears. The experiment does not behave as though the photon always had a definite little route independent of the measurement. It behaves as though the route becomes a meaningful fact only when the physical world contains the information needed to distinguish it. So when we ask whether the quantum eraser rewrites the past, we may already be smuggling in an assumption. We assume there was a definite past path to rewrite. We imagine that the photon must have gone through one slit or the other, or behaved as a wave or a particle in a fully settled way before the later measurement. But quantum physics may be telling us that this assumption is wrong. The photon's past may not be a complete classical route waiting behind the scenes. It may be a quantum history that only takes on certain classical descriptions when the full measurement arrangement is known. The delayed choice eraser makes this difficult because of timing. In ordinary thinking, timing is everything. First the cause, then the effect. First the match is struck, then the flame appears. First, someone presses the doorbell. Then the dog begins a dramatic announcement to the entire neighbourhood. We rely on this order constantly. So when a later idler measurement helps sort earlier signal detections into interference patterns, it feels as if the order has been disturbed. It feels as if the later event is reaching backward. But the actual data never lets us use the later choice to control the earlier result. That is the quiet guardrail that keeps the experiment inside physics rather than science fiction. If we look only at the signal photons, the ones that land first, we see no message from the future. The distribution does not tell us whether the idler photons will later be measured in a path-preserving way or a path-erasing way. It does not reveal a clean interference pattern by itself. It is only after the signal detections are matched with their entangled idler partners that different patterns appear. Some sorted groups show interference, other sorted groups show a complementary pattern. When all the groups are mixed together, the patterns wash out. This means the later measurement does not change the earlier signal screen. It changes how the already recorded events are meaningfully grouped. That grouping is not casual. It is not like randomly sorting socks and then claiming the drawer has revealed the secrets of the cosmos, though many drawers are mysterious enough. The grouping is determined by the entangled relationship between the photons. Each signal photon belongs to a pair. Its idler partner is measured later. The idler result tells us which subset of signal detections the event belongs to. The strange part is that these subsets have different wave-like or particle-like patterns, depending on whether which way information was available or erased. The signal dot is fixed. Its place in the quantum pattern depends on the pair. This is why the experiment is often said to affect the past, but with a very careful meaning. It does not affect the past by changing what was recorded. It affects the story we are allowed to tell about the past. If which way information is preserved, we can speak of the photon in path terms. If the information is erased, the path distinction is no longer part of the physical story, and interference can be recovered in the correlations. The question is not whether a later act alters a definite classical fact. The question is whether the classical fact existed before the measurement context made it meaningful. Here we reach a subtle but important difference between an event and a history. The signal photon's detection is an event. It lands in one place. That part is definite. But the history we attach to that detection, whether it travelled this way or that way, whether it belongs to a wave-like pattern or a particle-like pattern, is not always contained in the signal event alone. In the quantum eraser, the history is relational. It depends on the signal photon, the idler photon, the measurement arrangement, and the information preserved or erased. A single dot does not carry the whole tale by itself. This can feel deeply unsatisfying, because our minds love stories with clear roots. We want to know what the photon did when nobody was looking. We want to picture it travelling through space like a tiny bead, taking a secret road, then landing on the screen. If the photon creates interference, perhaps it went through both slits. If the path is measured, perhaps it chose one. But quantum physics gently keeps refusing the comfortable version. It tells us that the photon is not a tiny classical object wearing a strange costume. It is a quantum object, and its behaviour cannot always be translated into a familiar path through space. Some interpretations of quantum mechanics handle this in different ways. One view says the photon's wave function, its spread of possibilities, collapses when measurement happens, producing a definite outcome. Another view says all possible outcomes continue in different branches of reality, and we only experience one branch. Another focuses on the idea that quantum states describe information and relationships, not hidden little objects with complete private biographies. There are also approaches where histories themselves are assigned only under certain conditions, when alternatives are decohered enough to be treated as separate. The arguments can become very technical, and possibly not ideal for drifting gently towards sleep, unless one has unusual taste in bedtime reading. But despite these different interpretations, the experiment's central lesson remains steady. You cannot look at the delayed choice quantum eraser and simply say, the photon definitely had a classical path all along, and later we merely discovered it. That explanation does not capture the role of interference, distinguishability, and erasure. Nor can you say the future sends a controllable command into the past, because the experiment does not allow that either. The truth lies in a stranger middle ground. The quantum past is not always the same kind of thing as the ordinary past. That phrase, quantum past, deserves a moment. In the ordinary past, at least as we experience it, events seem settled. Yesterday's cup of tea was drunk or not drunk. The window was open or closed. The bus was missed or caught, often by a margin that feels personally insulting. But at the quantum level, when alternatives remain coherent and no record distinguishes them, the past may not contain a single classical alternative. It may contain a structure of possibilities, a set of potential histories that only becomes describable in one classical way or another when the measurement context selects the kind of question being answered. The quantum eraser makes this vivid because the same collection of signal detections can be divided into groups where different stories apply. In one group, which way information remains, so the path story is available. In another group, which way information is erased, so the interference story returns. The photon's earlier arrival is not changed, but the type of past we assign to that arrival depends on the later measurement of the entangled partner. This is not rewriting in the common sense. It is more like discovering that the past was not a single printed page, but a set of pages that only form a readable story when paired with the right key. Of course, even that metaphor can mislead. The quantum world is not waiting in a state of vague poetry until someone opens a box. It follows precise rules. The predictions are not fuzzy in the sloppy sense. They are exact in the statistical sense. Quantum mechanics can tell us with extraordinary accuracy what patterns will appear after many trials. The mystery is not that the theory fails. The mystery is that it works while giving us so little comfort about what is happening between preparation and measurement. It predicts the clicks. It predicts the correlations. It does not easily give us a picture of tiny objects with definite paths. One way to stay grounded is to remember the no-signal rule. If the experiment truly allowed the future to rewrite the past in a usable way, then a scientist could choose how to measure the idler photon, and thereby change what another scientist sees earlier on the signal detector. That would allow messages to travel backward in time or faster than light. But the quantum eraser does not permit this. The signal detector alone always shows a pattern that contains no usable information about the later choice. Only when the two sets of data are compared, using ordinary communication, do the hidden correlations emerge. The universe protects causality while still being deeply odd. This is a bit like receiving a stack of receipts with numbers on them that look random. Later, someone sends you a list telling you how to sort the receipts into different piles. Suddenly, one pile reveals a pattern, another pile reveals a different pattern, and the full stack had hidden both. The later list does not change the numbers printed on the receipts. But without it, the structure is invisible. In the quantum eraser, the later idler results act like the sorting key. The difference is that the sorting key is not just administrative. It is part of the entangled quantum relationship that defined which information existed in the first place. So when people say the experiment rewrites the past, it is worth asking what they mean by past. If they mean the recorded dot on the signal detector, then no, the past is not rewritten. If they mean the classical story of which path the photon took, then the answer becomes more delicate. The experiment suggests that such a story may not be valid unless which way information exists. If the information is erased, the path story is not merely unknown. It is not the right kind of story for that subset of events. In that sense, the past is not changed. It is revealed to have been less classical than we assumed. This can feel almost unsettlingly modest. After all the drama, the answer is not a simple yes or no. It is not yes, the future changes the past. It is not no, nothing unusual happens. It is that quantum reality does not fit into the ordinary categories that make those answers seem complete. The experiment does not let us edit history, but it does challenge what we mean by history when we talk about a photon. It says that a quantum object may not have a definite past path independent of measurement, information, and entanglement. That is not time travel. It is stranger in a quieter way. There is a reason the quantum eraser has become so famous outside physics. It touches a very human nerve. We all live with the past. We think of it as fixed, heavy, unchangeable. We remember it, regret it, celebrate it, and sometimes replay it at 2 in the morning when the mind decides that sleep would be less useful than reviewing an awkward conversation from 7 years ago. The idea that the past might not be fully definite feels almost personal. But the experiment is not about human memory or life history. It is about photons in carefully arranged conditions. The past of your kitchen chair is not waiting for an idler photon to decide whether it was wave-like. The everyday world is far too entangled with its environment for that sort of delicate ambiguity to survive. Large objects leave records everywhere. A chair reflects light, pushes against the floor, exchanges heat with the room, and becomes correlated with countless particles around it. Its position is recorded again and again by the environment. This constant leaking of information makes the chair behave classically. The quantum possibilities decohere so thoroughly that you never see your chair produce an interference pattern unless perhaps you're extremely tired and should close your eyes. The quantum eraser works only because scientists protect tiny systems from this ordinary flood of records, then control which information exists and which information is erased. That control is what makes the experiment so revealing. It strips reality down to a place where information itself can be handled like a physical ingredient. Preserve the clue, and the photon behaves one way. Erase the clue, and the wave-like pattern can return. Delay the choice, and the ordinary timeline of explanation begins to tremble. But the trembling is in our interpretation, not in the recorded dot. The dot stays still. The pattern emerges later through comparison. The past is not overwritten. Our classical story about the past is what fails. Perhaps the gentlest way to say it is this. The delayed choice quantum eraser does not show that the future changes what already happened. It shows that what happened, at the quantum level, may not be fully expressible as a definite path until the whole measurement context is considered. The event is real. The click is real. The correlation is real. But the simple phrase "the photon went that way" may not always be real in the same sense. It may be a story that only becomes valid when the experiment leaves the right kind of record. This is difficult, because language itself is built for the everyday world. Words like path, particle, wave, before, after, and happened all come from human-scale experience. We invented them for stones, rivers, footsteps, clouds, meals, and mornings. Then we carried them into the quantum world and discovered that they work only part of the time. The quantum eraser shows the seams. It reveals where our words stretch and where they tear. The photon is not behaving irrationally. It is our ordinary grammar of reality that begins to wobble, and yet this wobbling is not chaos. It is not anything goes. The experiment follows strict rules. The correlations appear exactly where quantum theory says they should. The interference returns only when which way information is erased. It disappears when the information remains. The timing can be delayed, but usable messages cannot be sent backward. The mystery is precise. That may be the most beautiful thing about it. The universe is not vague. It is exact in a way that our imagination has not fully learned how to picture. So does the quantum eraser rewrite the past? In the simple science fiction sense, no. No dot is changed. No timeline is edited. No observer reaches back and forces a photon to have done something different. But in the deeper quantum sense, the experiment does ask us to give up the idea that every past event at the smallest scale has a definite classical story, independent of measurement. It tells us that the past of a photon is tied to information, entanglement, and the way the experiment is completed. The past is not rewritten. It is not fully written in the way we expected. That is perhaps more unsettling than time travel, because time travel still imagines a classical world with a timeline that can be altered. The quantum eraser hints at something more delicate. It hints that the timeline of a quantum event may not be made of definite little beads before measurement. It may be more like a fabric of possible relations, becoming definite only where the universe keeps records. And when the record of a path is removed, the path itself is no longer the right description. The wave pattern returns not because the photon changed its mind, but because the conditions for saying which way have vanished. From here, we are led to the larger question behind the whole experiment. If information can decide whether a photon has a path or an interference pattern, then what does that say about reality itself? Is the universe made of things first and information second, or is information woven into the very structure of what things can be? Does observation simply reveal the world, or does measurement help define the world at the quantum level? These are not questions with easy bedtime answers, though they are very good at making the ceiling look suddenly philosophical. The quantum eraser does not solve them completely, but it gives us a quiet laboratory window into their depth. The quantum eraser leaves us in a peculiar place. We began with a simple question about light passing through two openings, and somehow we arrived at a question about whether the universe keeps a definite record of the past before information exists to define it. That is quite a journey for something as small and quick as a photon. It is like asking someone to explain a candle flame and being quietly handed the keys to a library, a clock tower, and possibly a locked room marked reality. The experiment does not give us an easy answer, but it does reveal something deeply important. At the quantum level, reality is not only about objects moving through space, it is also about information, records, relationships, and the strange conditions under which possibilities become facts. In the world we normally inhabit, information feels secondary. First, something happens, then information about it may be recorded. A bird crosses the sky, and someone may photograph it. A cup falls, and the sound tells us it broke. A person walks through a doorway, and a camera may later confirm which doorway it was. But in all these familiar cases, we assume the event happened in one definite way before anyone learned anything about it. The information reveals the fact. It does not help create the fact. That assumption works so well in daily life that we barely notice we are making it. It is part of the mental furniture of being human, along with expecting floors to stay solid and expecting the last biscuit to vanish mysteriously when no one is looking. Quantum physics asks us to be more careful. In the double-slit experiment, if there is no which-way information, the photon behaves in a wave-like way. Its possible paths remain together enough to interfere. If which-way information exists, the interference disappears. If that information is erased, the interference can return in the correctly sorted data. This tells us that information is not merely an after-the-fact description. Information is a physical feature of the experiment. A clue about the path is not just a note in our notebook. It is part of the quantum arrangement. When the clue exists, the alternatives are distinguishable. When the clue is erased, the alternatives can become indistinguishable again. That may be the central lesson of the quantum eraser. Reality at small scales is not made only of tiny things with tiny hidden roots. It is made of possible outcomes, physical records, and correlations between systems. A photon does not always carry a complete classical biography, as if it had a little passport stamped left slit or right slit. Whether such a statement even makes sense depends on whether the experiment preserves the information needed to distinguish the paths. If the path is knowable, the photon can be described in path terms. If the path information is erased, that description may no longer apply. The event is still real. The detector still clicks. But the story we are allowed to tell about the route is not independent of the information structure. This is a difficult idea because it sits between two tempting mistakes. One mistake is to say that the experiment is ordinary and nothing strange is happening. That is not true. The delayed choice quantum eraser is strange. It does challenge our everyday idea that every tiny event must have a definite path before measurement. It does show that erasing information after a signal photon has already landed can reveal interference patterns in the sorted correlations. It does force us to rethink what we mean by a quantum history. But the other mistake is to say that the experiment proves the future literally changes the past in a simple science fiction way. That is not right either. The dots do not move. The first detector does not receive a message from the future. No one can use the eraser to send a warning backward in time, which again is unfortunate for anyone who has ever trusted a suspicious sandwich. The experiment teaches something subtler. The past of a quantum object may not always be a fully definite classical story. We're used to thinking of the past as a row of completed facts, each one fixed and waiting behind us. But a quantum event can be definite in one sense and incomplete in another. The photon lands in one place. That is definite. Yet whether it belongs to a group showing interference or a group preserving path information depends on its entangled partner and the later measurement outcome. The dot is a fact, but its place in the larger quantum pattern is relational. It depends on the whole system, not on the signal photon alone. Information, then, is not a ghostly abstraction floating in the mind. It is physical. It can be stored in a detector carried by an entangled particle, scattered into the environment, or erased by arranging a measurement that removes the path distinction. This is one of the great quiet shifts in modern physics. We often treat information as something humans collect, but quantum mechanics shows that information belongs to the physical world itself. A record is a physical state. A distinction is a physical relation. A clue changes what patterns can appear. The universe is not simply made of matter and energy in the old sense. It is also structured by what can be distinguished from what. That idea reaches far beyond the double slit. In quantum physics, what matters is not only what exists, but what can be known in principle. If two alternatives are completely indistinguishable, they can interfere. If they are distinguishable, even by a clue no human ever reads, the interference is lost. This is why a stray interaction with the environment can make delicate quantum behavior disappear. The environment is constantly collecting which-way information about large objects. Light bounces from them. Air molecules strike them. Heat flows through them. Every interaction is like a tiny note written into the surroundings. By the time we deal with chairs, tables, teacups, or people, the world has written far too many notes for quantum interference between everyday alternatives to survive. That is why the world around us feels solid and definite. It is not because quantum rules stop working for large things in some simple way. It is because large things are entangled with their environment so thoroughly that their alternatives are separated into stable records. The room knows where the chair is, in the sense that light, air, dust, and heat all carry information about it. The chair is not delicately isolated like a photon in a laboratory. It is being constantly witnessed by the environment, though not witnessed in the human sense. No conscious observer is needed. The universe is full of physical interactions, and those interactions create records. In a way, the everyday world is classical because it leaks information everywhere. The quantum eraser works only because scientists can control that leakage. They can create pairs of photons, preserve entanglement, guide them along carefully arranged paths, and decide whether path information remains available or becomes erased. This is why the experiment is so powerful. It does not happen in the noisy middle of ordinary life. It happens in a carefully protected setting where the fragile rules of quantum possibility can be seen. The laboratory becomes a quiet place where information is handled almost like a material. Keep the clue, and one kind of pattern appears. Erase the clue, and another kind of pattern is recovered. Delay the choice, and the ordinary story of before and after begins to feel less secure. And then there is time. The delayed choice quantum eraser feels disturbing because it seems to put time out of order. The signal photon lands first. The idler photon is measured later. The later result determines how the earlier signal event is sorted. The ordinary mind says, "This is backwards," but quantum mechanics replies gently and rather unhelpfully, that the full event was never just the first photon alone. It was the entangled pair, the measuring arrangement, and the correlations revealed when the data was brought together. The apparent backwardness comes from trying to tell a quantum story as if it were a classical sequence of little billiard balls. This does not mean time disappears completely. The experiment still happens in a laboratory. Detectors click at times. Records are stored. Data is compared later. Scientists still need clocks, cables, patience, and probably coffee. But the meaning of a quantum event does not always fit neatly into our preferred timeline. We want to say the photon first did something, then later we found out what it did. The eraser suggests that in some cases the question what it did is not fully meaningful until the entire measurement context is included. The past, in this narrow quantum sense, is not a simple hidden road. It is a set of possible histories whose classical description depends on what information exists. This is why the experiment feels so close to philosophy, even while it remains a physical experiment. It asks what a fact is. It asks whether a path exists before it can be distinguished. It asks whether a quantum object has a history independent of measurement, or whether history is partly defined by the records that connect events. These are not just word games. The answers show up in patterns on detectors. They show up in interference and its disappearance. They show up in the restored wave patterns that appear only after the data is sorted by entangled partner outcomes. Reality is not giving us a metaphor. It is giving us measurements that force metaphor to struggle. Different interpretations of quantum mechanics take this lesson in different directions. Some physicists are comfortable saying that measurement causes a collapse, turning many possible outcomes into one actual outcome. Others prefer to imagine that all outcomes occur in branching realities, with each measurement dividing the world into separate histories. Others say the quantum state represents information about relationships between systems, not a private hidden picture of things as they are in themselves. Some approaches avoid deep claims and simply say, here are the rules, here are the probabilities, here are the results. This is a respectable position, especially if one would like to sleep at some point. But whatever interpretation we prefer, the quantum eraser keeps pressing on the same tender point. It tells us that the difference between wave-like and particle-like behavior is not just about the photon itself, it is about the information available in the experiment. It tells us that entanglement can spread the meaning of an event across more than one particle. It tells us that delayed measurement can reveal patterns that do not fit easily into a simple chronological story. And it tells us that the universe at small scales may not be built from definite facts in advance, at least not in the way our everyday language imagines. This does not make reality unreal. That is important. Quantum physics is sometimes described as if it makes the world vanish into imagination, as if nothing exists until someone looks, or as if human consciousness is painting the moon into the sky every night. That is not what the quantum eraser shows. The moon is not waiting nervously for attention. The world is not a dream created by observers. The experiment shows that very small, carefully isolated systems do not always possess definite classical properties before measurement. It does not show that ordinary objects are fantasies. It does not show that thoughts alone create physical facts. It shows that physical information and measurement matter in ways classical physics did not expect. In fact, the quantum eraser may make reality seem more precise, not less. It shows that the universe obeys rules even when those rules are strange. The interference returns only under the correct conditions, which way information removes it. Erasing the information restores it in correlations. Delaying the eraser does not allow a backward message. The whole thing is delicate but not sloppy. Nature is not improvising randomly. It is following a hidden grammar, and the grammar includes information as a real part of the sentence. Perhaps this is the best way to hold the meaning of the experiment. The quantum eraser reveals that reality is not simply a collection of separate objects with pre-written stories. It is a web of relationships, possibilities, and records. A photon is not merely a tiny bead travelling through a slit, it is part of a quantum arrangement. Its behaviour depends on whether its possible paths remain indistinguishable, whether a clue marks them apart, whether that clue is preserved or erased, and whether an entangled partner later reveals the pattern. The object cannot be fully separated from the question being physically asked. This may sound unsettling, but there is a quiet beauty in it. The universe is not crude. It is not made only of little mechanical pieces clicking through predetermined grooves. At its smallest scales, it seems to be made of a more delicate order, one where possibility is real enough to interfere, where information is physical enough to change outcomes, and where time is not always the simple stage on which events perform. The delayed choice quantum eraser does not show that the future bullies the past. It shows that the past of a quantum system may be woven from information that is only meaningful in the full fabric of the experiment. And what does that mean for us here? Far from the laboratory, perhaps under a blanket, perhaps listening while the room grows quieter, it means that the universe is stranger than the everyday world suggests. It means that beneath the steady surfaces of things, beneath clocks and lamps and curtains and the gentle shape of a familiar room, there is a level of reality where certainty is not always waiting in advance. There is a level where possibilities overlap, where records matter, where knowing and being knowable are not the same, and where a photon can make us question what it means for something to have happened. We should not take that lesson too far. Your past is not a quantum eraser experiment. Your memories are not waiting for an idler photon to sort them into interference bands. The ordinary world is full of records, and those records give life its stable shape. But the experiment does offer a humbling reminder. The reality we experience is not the whole of reality. It is the large-scale version, the record-rich version, the version where the environment has already done most of the measuring for us. Deep below that, nature is quieter, stranger, and less committed to our familiar categories. Maybe that is why the quantum eraser is so fascinating. It does not simply answer a question. It changes the kind of question we think we are allowed to ask. Instead of asking, which path did the photon really take, we are invited to ask whether the experiment preserved a path at all. Instead of asking whether the future changed the past, we ask whether the past was ever classical before the information existed. Instead of asking whether light is a wave or a particle, we learn that wave and particle are not final identities, but different faces revealed by different arrangements of information. And so, after all this, the quantum eraser leaves us with a softer but deeper mystery. Reality may not be a finished picture hidden behind a curtain, waiting for us to pull the fabric aside. It may be more like a pattern that becomes definite through interaction, a pattern shaped by what can be distinguished, what is recorded, and what remains connected. The universe does not need human eyes to exist, but at the quantum level, it may need physical records for certain facts to become facts at all. That is not magic. It is stranger than magic because it is measurable. We began with light passing through two openings, a humble arrangement that could almost be built from silence. We followed photons as they behaved like waves, then particles, then something deeper than either word. We watched which way information destroy interference, entanglement carry the clue away, delayed choice unsettle the order of events, and erasure restore the wave in hidden correlations. And now we arrive not at a simple conclusion, but at a quiet recognition. The quantum eraser does not tell us that reality is unreal. It tells us that reality is more subtle than the version our senses evolved to handle. So, dear listener, wherever you are, and whatever time it is in your corner of the world, perhaps this is the gentlest place to leave the mystery for tonight. A photon does not rewrite the past like a careless editor, but it does show us that the past, at the quantum level, may not be written in the fixed ink of ordinary things. It may be written in possibilities, in records, in entanglement, in the fragile grammar of what can and cannot be known. And while that may be difficult to picture, it is also quietly wonderful. The universe is not only vast above us, it is strange beneath us, around us, and even inside the light by which we see. If this journey through the quantum eraser brought you a little calm, a little curiosity, or simply a softer way to think about the strange world beneath the everyday one, then I would be grateful if you liked the video and subscribed. It helps this sleepy space of science reach others who may enjoy resting beside the mysteries of physics. And now, as the thought of photons and paths begins to fade, let the question loosen rather than tighten. There is no need to solve the universe tonight. Let the experiment rest in the background like a quiet lamp. Let the world become simple again for a while. The room is here, the night is here. Your breathing is moving gently forward, one moment after another, and somewhere, in the deep small places of reality, light is still keeping its strange and delicate secrets.